an incredible honor for me to be able to introduce Marc Lanctot. He's a research scientist at DeepMind, the Canada branch. Is that right? He got his PhD from University of Alberta in 2013. And he's known for his contributions for artificial intelligence in games, particularly games of imperfect information, which are mostly the interesting ones. One reason I'm so honored to be able to introduce him is because I worked at a game company this summer, and basically anytime we're trying to design, we were trying to build AIs to play our games. Every time we're doing this, we'd be reading a paper that had Marc's name on it. It's pretty cool to see how he's taken really old school ideas from game theory, some as old as like the 50s, and been a part of converting them to a modern machine learning language. So pretty much any of the cool stuff you've heard of that's come out of DeepMind, he's had some part in it, at least on the game side. So if any of you have heard about the recent advances in StarCraft, Marc presented the general algorithm that characterized the way they had their populations of agents learn to play stuff. Those of you haven't heard about that, their agents just achieved Grandmaster level in competitive StarCraft with human-like constraints, so really impressive. Anyway, most recently he's been interested in, I think, spreading this, having a lot of breadth in his work, and he's introduced this new framework, OpenSpiel, which is a library for games to improve information. I think we're all going to learn about it. So without further ado, please welcome Marc Lanctot. Presenting you.
Awesome. Thanks for that wonderful introduction. So today I'm going to tell you about multi-agent reinforcement. It's a broad topic, and a lot of people would define it differently. I think that's partly what makes it interesting. It's partly also what makes it so hard. Just a quick workshop plan for the day. So I'm going to start with a 15-minute workshop intro. Partly this is for me to get to know you a little bit better, also for you to get to know me a little bit better, and to get to know a bit about your background. So I want to make sure I sort of talk at the right or at the optimal level of abstraction if I can. Okay, so I'll just go through a little bit about what the plan is. After the intro, the first 2 hours or hour and 45 minutes will be extremely high level, like a tour through multi-agent R. So multi-agent reinforcement learning has existed since early 90s. There's been lots of work that's been done on it. I'm really gonna go over it like a real a glossy overview of what it's all about, with a little bit of introduction to the formalizations, right? And why and what the problem is in multi-agent R, and what we're trying to solve. But it's kind of like a historical perspective. Okay. Then after that, we'll take a bit of a break for lunch, and then we'll do a bit more of a deep dive. So two specific problems that I'd like you to understand in adapting single-agent reinforcement learning to multi-agent, specifically to zero-sum games. So that's I have a lot of experience with zero-sum games. We'll take a coffee break after that, and then we'll do like a bit of a practical session using OpenSpiel, where we can actually see some of this stuff in action. Okay, so that's the rough idea. The first thing I always like to start with thanking my a lot of great collaborators. I'm very fortunate to work at a place where we can work with the same people over and over again. And actually, this talk is the first time I couldn't fit them all on one slide. So I really want to thank all these people. Really, a lot of the stuff I'm going to tell you today is not really just me pioneering all this stuff, right? It's really the work of a lot of different people. So I apologize in advance if I have to say I don't notice something because it's a detail that one of my collaborators worked on. But I think that's really a testament to like the kind of environment we have at DeepMind. We can really pool all our resources and work on really great projects because we have a lot of people. So here you go. First slide, second slide, a little bit of overlap there. Okay, so introduction to the workshop. What are we going to do today? I'm going to start by pulling your knowledge a little bit. And that's only because I want to get an idea of the sense of kind of things that you know about RL and about machine learning in general. So who has seen this book before? And maybe who has read this book or used it for a course? Okay. Yeah. So just Rich Sutton, the first author of this book, is actually the head of DeepMind Alberta. So that's where I am now. I'm in DeepMind Edmonton, and there's 2 offices in Canada, one in Montreal and one in Edmonton. And we're lucky that our Edmonton lab is actually led by the father of reinforcement learning, which I'm very fortunate to be there. Okay, so a quick survey of topics. So I'm going to list a bunch of topics now. I should have said, sorry, I didn't start with something that I always start. I really don't want this to be 6 hours of me talking. I would really please interrupt me. I love being interrupted, and I love being asked questions. So if there's any time, and even if the question is a simple question, please just raise your hand and ask it. Okay. I would like nothing more than for this to be an entire 6 hours of interaction between all of us. That's what I'm hoping to get out of this. There's 2 specific things I would like that you have learned by the end of today. And I'll absolutely get to them. So don't be scared to add. If there's a diversion, that's a success in my opinion. There's always stuff that I can cut out that's not too important. Okay, so if I'm going to list a bunch of topics now, and I want you to raise your hand if you feel that you know the topic or the concept well enough to be able to describe it to somebody, to be able to kind of broadly teach it to somebody. You don't have to get it perfect. But you feel without having to refer to a textbook that you can explain this topic to somebody. Does that work? Understood? So I'm gonna list about 10 different topics now. Unbiased estimator. I started with that one because I figured pretty much everybody here would do that. Okay. Importance sampling. Okay. Markov decision process. Either one of these, Nash equilibrium or minimax theorem. Okay. Regret minimization, which has also been called by many other names. No regret learning, Henan consistency, universal consistency. I'm very happy with that one. So one of the 2 things I'm going to tell you about today is a story about regret minimization, and we're going to go into some amount of detail. So I think one of the things you're going to learn the most is why regret minimization has been important for imperfect information. Okay, generalized policy iteration. Okay, reinforcement learning. I guess I already had that question. The difference between value-based RL and policy gradients. Oh, that's surprising. Okay, cool. Monte Carlo tree search or minimax search. Function approximation or a neural network. Okay. A proof by induction. Who has actually done a proof by induction? Yeah, I asked a specific question because I'm never sure whether that's a computer science specific thing. We do tons of these in computer science. And yeah, so I just want to get a feel for that. Okay, thank you for going through that. I really got a good idea of where your knowledge sits. So I have a much better idea of how to steer this. Okay, so we're going to start off with 2 games. Well, actually, one's not really a game. The first one's a game. The second one's more of a poll because I kind of want to get to know a little bit more about you. But I don't want to go through and ask you tell me what you're doing as we're doing this. So here's what we're going to do. We're going to play the first game. This is where you're going to use your 2 pieces of paper. And the only thing I'm going to ask you is that you don't use any Wi-Fi or shut off your data or whatever. Don't use the internet to answer the question. I'm just going to give you one. It's not a hard question. I'm going to describe to you a game. And what you're going to need to do is write something on a piece of paper. And you're going to hand those pieces of paper to me. And we'll figure out who wins maybe at the end of the day. So here's the game. You have 100 actions. No, you have 101 actions. You can write down any number between 0 and 100. You put that down on a piece of paper and you're going to hand that in to me. The winner of the game is going to be the closest to whoever guesses the 2/3 of the mean of the values. There's going to be a mean of these values. That's well defined. You can tell you exactly what that is. Whoever's closest to 2/3 of that value is going to win. So one central concept in game theory is the Nash equilibrium. And the Nash equilibrium is this concept where I want to play with a policy, I want to play with a strategy where I have no incentive to deviate from what everybody else is doing, right? And that's exactly what you're describing. So you thought of a policy because you were conditioning your actions on some assumption of how other players would play. You thought what the right move is based on that assumption, and then you questioned that assumption because if they knew what you were going to do, they would do something different. This game really captures exactly what's fundamentally interesting about multi-agent learning. So the question of like what should agents do? This game captures it all. Okay, great. Thank you for entertaining that. We'll say who the winner is after. We'll talk a bit about Nash equilibrium in this talk. All right, so a little bit about me. Thank you for participating in those two small games. I'll tell you a little bit about what I care about in research. What I've been doing in the last few years is harmonizing reinforcement learning and computational game theory. That's sort of like the thing I care about the most right now. And part of the reason for that is because I have a background in computational game theory. So I worked on algorithms to efficiently compute Nash equilibria two-player zero-sum games. That was kind of my research history coming into DeepMind. I also did a bit of Monte Carlo tree search. And when I got to DeepMind, it was really funny because I had always kind of been interested in reinforcement learning, but I had never really worked on it in enough depth to say that I really understood it. And part of that was a bit of a language barrier in terms of like the concepts that we used were being referred to using under different names. And the terminology was a surprising barrier there. Like for example, I think I got a question earlier. Are we going to have any off policy? Are we going to be talking about any off policy methods today? When I was first reading the reinforcement learning book, I did not realize how important the distinction between off and on policy was. I didn't know why it mattered. So those kind of things. Because I never really worked in reinforcement learning, I never really had like sufficient understanding of what reinforcement learning was, or what the algorithms were doing in the background, what their limitations were. When I came to DeepMind, that all changed because I was surrounded by people who were interested in reinforcement learning, who could tell me answer exactly those questions. And I felt I had something to offer to them, which was a little bit about computational game theory and multi-agent reinforcement learning. And what happened was I became interested. The more I found out, the more I realized there's a lot more in common between these two fields, despite the fact that their communities are not really always. Okay, so here's what I care about in research. I kind of phrase it. I kind of categorize multi-agent RL in its 4 quadrants here. And you can think of the y-axis as sort of the scale of the problem, and you can think of the x-axis as it's a binary x-axis of either single agent or multi-agent, and really the multi-agent side is kind of going to be 2 players or some, so it's a very small part of multi-agent, but it's mostly going to imply this abstraction is going to be mostly okay for what I'm going to tell you. So if you look at the way I see this left side is this is the RL book, Sutton and Bartow, 2018, second edition. It kind of starts off with the foundations like dynamic programming, generalized policy iteration, MDPs, value functions, these kind of rewards, exactly. And it's something I like to phrase, I like to put into, I like to call approximate dynamic programming, the core of value-based RL. And the more you go through the book, the more you find out how you're going to scale these techniques. Function approximation, n-step bootstrapping, these kind of things. So it's like going through this book is just going up here. And I think the important part for what I'm going to say next is that there's this foundation. There's a foundation where the algorithms are resting on. Convergence guarantees are in the background, and those are important, and they're different in the multi-agent case. So the first era of multi-agent reinforcement learning, so early to mid 90s, no, maybe early to late 90s, was trying to do this. Was basically trying to understand the foundation of what it means to do multi-agent reinforcement learning. Coming up with a lot of algorithms that worked on these tabular solution methods. A lot of what we're doing now, so I call this the second era of multi-agent RL, is taking a lot of the solution methods that have worked at scale and bringing them in to the multi-agent case, and seeing a lot of success. Here's kind of what I want to do and what the talk is going to be focused on. I think that we need to, I think the foundations of multi-agent RL are important. This bottom right quadrant here, I tend to think of game theory as the sort of language that's going to formalize everything. And what I'd like to do is go back to these game theoretic formulations and try to see if we can scale them the same way, but starting from the foundation. Okay. So really, my 10-year mission is to create the Introduction to Multi-Agent RL, which is the book that sits on the side. Okay, so that's a little bit about me. That's what I care about, and that's sort of why I'm here. Something that you need to keep in mind today is that there's this difference in terminology. So the games community talks a lot about players and strategies, utilities, payoffs, maybe moves. I'm almost exclusively going to be using the reinforcement learning terminology, but they largely mean the same thing. So when I say policy, I really just mean strategy. So like a policy is just a way to play. It's how you choose your actions. I'm going to probably use reward. I'll use information state a lot because I'm going to be talking about perfect information games. But so just keep that in mind. I think the policy one is the most important one. So when I say policy, what I mean is really just like a function from an agent's state to its actions. Could be a distribution over actions, could be a deterministic mapping, whatever. Okay, that's really the intro. Any questions up to this point? No? All clear. Okay, so intro to MARL. Here's what we're going to do. So this is the first section. What is multi-agent reinforcement learning? A bit of foundations, trying to get you to understand the problem formulation, and a quick overview of all the algorithms that exist in this space. Okay, so multi-agent reinforcement learning. It is all about agents trying to learn together. So here's two examples. This is Palmer. It's partially observable. It might not look partially observable because we've given it an overhead view, but it's a competition that's been run at Neuros last year, this year as well. Each agent is trying to coordinate to collect a bunch of these items here. And they have certain resources and they can blow up the walls, and they have to do this together. Laser tag is another one. Laser tag was an environment that we worked a lot with in our first experiments at DeepMind. Each one of the agents is trying to find the other agent and tag them. If you tag the other agent, you get a point of reward, and then that agent resets at one of the spawn points. So again, this one was partially observable, even though it doesn't seem so because we're giving you an overhead view of the map. In this case, each agent had like a little viewport that they could see around them. They didn't see the entire map. Almost all the games I'm going to talk to you about, or environments I'm going to talk to you about today, actually have partial observability. That's the thing I'm most interested in. I think it's the most realistic setting for multi-agent RL. It poses a real problem when you do it in the multi-agent case, which I think you'll have an appreciation about at the end of today. Here's other kinds of multi-agent RL problems, very high level. So traditional single agent reinforcement learning, you might have seen this. This is on Wikipedia, but there's similar ones in the RL textbook. An agent is essentially interacting with its environment. The way it does that is by presenting actions. As a result of acting in the environment, the agent sees things. It gets a reward, and it interprets its new state or its observation. So this is the idea behind single agent reinforcement learning, and the idea is that you use algorithms here to learn how to act based on the rewards. Okay, what is multi-agent RL? Multi-agent RL is very similar, right? In fact, you can almost think that I've vectorized the agent in some sense by having multiple agents. But each one of these is an actor or decision maker or learning algorithm that is receiving observations and rewards, and together putting actions, and the joint action goes to the environment, and the environment gives back observation. That a few years later, the Artificial Intelligence Journal devoted an entire journal issue to answering that question. So it said, okay, we're gonna take papers that attempt to answer this question. So here's some of the answers. Here's some of the papers that came out of this. So an economist's perspective on multi-agent learning, perspectives on multi-agent learning. These are all people that are prominent contributors to this field. Agendas for multi-agent learning. Multi-agent learning is not the answer, it's the question. What evolutionary game theory tells us about multi-agent learning. All these papers that we're trying to rally the community around saying, look, we need an answer, and we kind of need to figure out what multi-agent reinforcement learning is before we continue working on it. Otherwise, we're really just working on slightly separate problems and we're not getting it. Okay, so I'm just going to summarize some of the broad axes that multi-agent RL sits in. And the reason for this is to kind of explain which one we're going to sit in today. So there's at least 3 different methods or ways that we can think about multi-agent reinforcement learning. One of them, one axis is this centralized versus decentralized. So a centralized method, and this is just to get you familiar with some of the terminology because I'm going to be using it later. The centralized method is you have one algorithm that's basically learning everything for all the agents and putting the policies on the agents and expecting that they're going to act together. Right? So this might be like if you're trying to build a house and you have multiple agents, the ultimate goal is to build a house together, right? But you have all these agents that are experts at different things, and you could do this centrally, right? Because you're the designer. The whole point that the whole reason for running this experiment is building this house. The decentralized view is saying, wait, no, hold on. Agents are themselves the learning algorithms. They do not get to actually coordinate, or they don't get to know. It's not that one central learning process is going to be doing all the work and handing it off to the agents. No. The whole point of this is to be distributed or decentralized. Okay, so that's one sort of difference, right? Those are 2 separate problems. Probably this is the axis that's the most important for today. So there's the prescriptive setting and the descriptive setting. Prescriptive setting is trying to answer the question of how should agents act? What should agents be doing and why should they be doing it? So this is the one that I'm normally a part of because I'm an algorithm designer, right? I am trying to explain why agents should be using certain algorithms over others. And we're going to formalize some of the properties that we would like to have in our learning agents. But there's another agenda, they call them, or view on multi-agent RL, which is the following. I can't control what the agents are doing. They're using some form of learning algorithm. What I'd like to know is how they're going to act together, right? So if they're all using Q-learning or DQN or whatever algorithm you want, and they're going to go out in the world and they're going to interact, what's going to happen, right? That's an important problem. It's definitely not the same problem as trying to design an algorithm for each one of the agents. Okay, so then we can actually split it up in how the agents are incentivized. So what is their utility? Are they cooperating? Are they competing? Are they doing neither? Are they both cooperating and competing? So anyway, this is a bit of background just to tell you that we're mostly going to fixate on one setting, which is very common in multi-agent RL, which is we do centralized training for decentralized execution. So normally the case is you have learning algorithms that have a training period. In that time, they're central. They're allowed to communicate with each other. But the idea is that you pull out the policies they've learned, and they're going to go off into the world and not be able to communicate, right? So the idea, one application of this could be like a simulator. If you're trying to learn like a self-driving car, you build a simulator, self-driving cars, learn in your simulator, and they get you a policy that you can then go apply on a real car. Now, that's a lot harder than it sounds. Maybe it sounds hard. So we're going to deal mostly with the prescriptive setting. We're going to talk about algorithms and why we want our agents running these algorithms. And because I'm mostly experienced with the competitive setting, we're going to be talking mostly about the competitive setting, but I'll sprinkle in a bit of the cooperative and general sum. So, okay, a bit of foundations and background. This is an important book. If you're interested, there's unfortunately like no real good book for this specific topic. There's a few books that have come out on multi-agent RL. There's not. I think we need a book now that kind of introduces it in the same way that Sutton and Bartow introduced single-agent RL. But most of what I'll talk about will be you can, if you're interested in this topic, I would say go off and read this book. It's a very good reference. Okay. So what are the foundations of multi-agent reinforcement learning? So I'm going to go really simple. And I'll try to describe a very simple setting, like the game that we played. Enough to be able to describe what the optimization problem is. Okay, so I'm just going to go into a little basics of game theory. Okay, so normal form or one-shot games, also called strategic games. You have a set of players, and I'm going to use a little bit of notation. Oh, I didn't hand this out, but I'll hand it out later. It won't be referenced for the first. It won't be relevant for the first part. I have a handout that will have some of the notation on it for the second part of today, where we actually work out some problems. For now, this is mostly standard notation. So a player and a subscript I, or just the letter I, will always refer to a player in today's talk. Capital N is the set of players. Each player, so I'm going to just describe to you a normal form game now. Each player has a joint set of actions, so subscripted by player I's, some discrete set of actions. There's a set of joint actions, which is just the Cartesian product. There's a utility function that basically maps any player and any joint action to some utility, which we'll just say is a subset of the reals. Okay, what do these look like? They typically look like this. So this is a bimatrix game, also just a two-player normal form game. And the way you want to interpret this is there's a role player and there's a column player, and they're playing at the same time. Okay, so that's a bit of a restriction, but we'll get rid of that later. And the way to interpret this picture is that if the role player has two actions, the column player has two actions. If the role player chooses action A, and the column player chooses action capital A, then the role player will get 0 utility, and the column player will get 0 utility. Okay, so this is an interesting game, maybe. So here are the actions, like I said, the utility to the role player and utility to the column player. For joint action, so there's 4 joint actions here. Yep. Okay, so the question is, how do you want to play this game? So the reason I put this down, the reason I'm starting really simple here is because I actually want to tell you what the agents are trying to do, right? So the agents are looking for a policy that maps to, in this case, it's like there's no states even. So it's just a distributional relation, think of it that way. That in some sense maximizes their utility, right? Okay, so let's actually try to really formalize that. Okay, so here's my attempt at doing that. Player, oh yeah, pi is going to be used for policies, like in reinforcement learning. So player I is trying to find a policy in, and this is just a set of distributions over their actions. Okay, such that they're maximizing something. right? And this is where things get interesting. So they're maximizing some form of expectation. The expectation is going to be an action drawn from the joint policy. So all players are playing with a policy, and they're maximizing their own utility value for taking the action A. Okay. Does this make sense? I mean, this seems like a good thing to do, right? There's a major problem with this. Maybe it's obvious. This guy is a joint policy. So player I is defining its optimization problem with respect to other players' policies. That's going to be a problem. That is actually the essence of multi-agent learning. I cannot think of maximizing a value independent of what the other players are doing. That's exactly what can't happen. That's the formalizing this optimization problem. You can't do it without considering what the other agents are doing. Okay? It's necessarily a function of the other player's policies. So if I had to pinpoint one main difference between single agent RL and multi-agent RL, it's exactly this, right? And the amount of trouble this causes is unfortunate. Also makes it much more interesting than single agent RL. Just my opinion. Mm-hmm. Okay. So now we've actually formalized the problem. How do we solve it? Okay. Let's think of the simplest way, right? Because I've just motivated that it's a hard problem because you actually don't have control over your other agents, right? So how do you even start, right? Well, you got to start somewhere. And let's start all the way back to the 1950s, as Alex was saying. Okay, so let's formalize a few important notions. Suppose player I. Let's relax the problem. We can't fully solve this problem, obviously. So we're going to relax the problem. We're going to say that the other players are fixed. That's actually the strongest relaxation, right? That's actually going to turn our multi-agent problem into a single agent problem, which is fantastic because then this expectation is easy to compute because the other players' policies are fixed. Okay. Oh, and a bit of sort of conventions. Minus I usually refers to the set of players, but excluding I. So minus I just is like the set of other players. Okay. Okay, so let's try to define this beast. So here's our optimization problem again. And what did I just say? I'm going to try and convince you that actually this becomes easy at this point because this expectation now is not really over the joint profile because the other parts of the joint profile, the joint policy, are actually fixed. So this thing is only doing an expectation over player I. So then you just have to search the space of policies for player I and you're done. Right? Okay, that's kind of easy. So there's a word for this. If you're maximizing this expectation when the other policies are fixed, it's called a best response. So the policy for player I is in the best response, and the terminology, notation we use, it's a best response to the set of other players' policies. That is the same, or that policy, that's actually a definition. That policy utility that it's achieving is the maximal utility that you can achieve against those other fixed policies. Does all make sense so far? Okay, we just call this thing a best response. Okay. We haven't solved our problem yet. We've just made it slightly easier. And it just turns out there's a bunch of algorithms that are based on this idea of best response. Okay, so let's go back to this matrix again and see what we can do with our new tool of best response. Well, we can start here, and we can ask ourselves, is this a good policy? Actually, we could play the game that we played this morning, which is, if I play this and I expect the others to play that, we would all get zero utility. But now if I play this, do the other players have incentive to move away from their strategy? So if I'm the role player and I choose small b, I expect the column player to use capital B, we're going to end up with 0, 0. Okay. So then I could just inspect the utilities and say, well, if I'm using small b, would the other agents want to change? Okay, and the answer is yes. If we actually have both, we both have incentive to change. So if I play B, if I assume that the column player is playing capital B, and I play small b, then I have incentive to move over to play A because I would get a utility of 1 versus utility of 0. So I have incentive to go that way. So it can't possibly be Nash equilibrium, or it can't possibly be the optimal way of playing because I can get more. Right? Same thing with the player D. Player D can go and get 1. So this can't be really a fixed point of this process. So in some sense, it's not solving that optimization problem I was saying, because all I've done is show myself that I have incentive to move away. Okay, so let's move to one of these. Okay, let's play this one. Are we done? No. Because there's still at least one agent that has incentive to move away from that. Right? So this is a really easy way to find a pure Nash equilibrium, which is here. Basically, this thing is a fixed point of this process. There's no reason to deviate from this point. So this is really just an example of what the agents are thinking when they come to make decisions in this multi-agent setting. This thing is known, well, this specific point here is a Nash equilibrium. It's a pure Nash equilibrium in the sense that what pure Nash equilibrium means is just it's a deterministic policy. Both players play AA. Of course, you have other things. So it's achieving this by pure chance. You have other games in which you can't actually achieve, you can't actually do this in the method using the method I showed just now. So if you look at this game is constructed exactly so that if you started here, you would move there. If you started here, you would move there, and you would so. Okay, so we've defined, what have we done? We've defined something called a best response. We've made our problem a bit easier. I showed you how in certain classes of games you can still get to a fixed point, which is a solution to this optimization problem. But I've showed you at least one game where you can't do it that way. Okay. So what do you do in this case? Well, let me tell you a bit more about best response. So a Nash equilibrium is a joint policy where no player has incentive to deviate. We saw that before. In other words, all the players are playing their best response. That's another way of defining Nash. If they weren't playing their best response, they would have incentive to deviate, which means it's not Nash. And just a few facts. If you want to find Nash, seems like Nash is a good thing to find them. It can be computationally hard. So this is just a few facts. If you want to use Nash equilibrium as a central concept for what your agents are doing, it's good because it exists. That's great. In two-player zero-sum, it's actually polynomial time to compute in the size of the description of the game. So that's great. It means we have efficient algorithms for doing it. Unfortunately, outside of two-player zero-sum, it is actually hard in the computer science sense of hard. Yeah.
Oh yeah. So in games, are there several Nash equilibriums, or just?
In general, yes. In general, yes. It can be infinite. There's a property that I'll get to later in zero-sum games, where if you're playing a Nash equilibrium in a zero-sum game, and somebody you're playing against is also playing a Nash equilibrium strategy in a zero-sum game, that you're guaranteed to get a minimum level of utility. That's a special case of zero-sum games. But your question is very relevant because in outside of zero-sum games, there's this problem called equilibrium selection problem, which means I could be playing in an equilibrium, you could be playing in a different equilibrium, and we put our strategies together and there's no guarantees at all. So that's going to be an unfortunate problem. Yeah, so computing a Nash is actually hard in the same like NP hard sense. Hard. We don't know any like efficient algorithms to do it in polynomial time outside of two-player zero-sum. But we can. There are tractable subproblems, and so computing an approximate Nash is something that we can do somewhat efficiently. The properties of the Nash equilibrium, it assumes unbounded power for each one of the players. So if I'm playing with a policy, I'm assuming that the other players are playing with the maximal policy that beats me. Right? That's what a definition of best response is. Is that good? Maybe. In some cases it's good. Some cases it's a bit too restrictive. So we'll see a bit of that too. It also assumes knowledge of the value function in the game. And it also assumes that all players are rational. Okay? So it's going to compute a policy under the assumption that my opponents are unboundedly rational, and they're also trying to compute their expected utility, and I know their utility. So there's a lot of restrictions there, and I mainly put this here to show you that like Nash equilibrium is a nice concept, and it's going to be optimal in some sense in 2-player zero-sum games, but keep in mind that outside of 2-player zero-sum games, it's a lot more subtle than that. Okay, so 2-player zero-sum. So let's go back to our example that we couldn't solve before. We can actually solve it, and we can do it in polynomial time. And here's how we're going to do it. We're going to say that the role player is maximizing a value of some form. Okay, so maximizing a value, right? And now I'm going to put a bunch of constraints. I'm going to say, well, that value has to be greater than. So this is actually what we're going to do is we're going to treat this thing as a lower bound, right? I'm going to actually try to maximize the value, which is a lower bound, and I'm going to compute that lower bound in a specific way. I'm going to go through each one of my policies. I'm going to go through the column splitters policies, deterministic policies. And I'll tell you why I can do that. So I'm going to say if the column player is playing big A, what would I get if I play policy pi? And this is the expected value of policy pi. I would take action A with probability pi of A. That gives me a +1 and then a -1 for playing pi. So that's if the column player is playing with big B. So I'm gonna express these constraints for each one of the deterministic policies for the column player. So so big B, the other one we just change the signs, and we're trying to find a policy such that against any one of the other players' policies that we're guaranteed to get this value in V. Right? Okay. We're also going to say we're going to put in constraints that the policy is an actual policy. So it's a probability distribution, so it sums to 1, and each one of them is greater than 0, or sorry, non-negative and not greater than 1. And yeah, so does this actually find that? So does this constraint problem realize that? It's not super obvious yet, but at least we've expressed some problem where we're trying to maximize our value V, and we're enumerating the number of things the opponent can do, and trying to express how to achieve that value. Okay, so here's a really key piece of computational game theory called the best response condition. For any stochastic or joint policy that the opponents could be using, there exists a deterministic best response against it. So it doesn't matter what other players are using. If I want to compute a best response to it, I can do that by just enumerating my deterministic policies. Okay, and the proof goes, if that wasn't the case, then you have an incentive to switch over to some of the other things that you're mixing over, right? So I can essentially just enumerate all of my deterministic policies, and I know there's a best response in there. So if I'm looking for something that's a Nash equilibrium, that's why I can go back to this optimization problem, and I don't need to search the entire space of the column player in terms of their stochastic policies. I can just literally just go through every one of the deterministic policies, right? Okay, so what is this thing? Does that make sense? I went through that really fast. This is actually a key condition. You can't build this constraint problem without it. Okay. Now, what is this thing? This is a linear program, which is beautiful because we can solve linear programs in time polynomial in the size of the description of the problem. Okay, so what is the solution to this one in particular? Well, if you look at the paths for a little bit and you stare at them, you'll see that V is 0, and that each player is using a policy of 1/2, 1/2. So this brings us to an interesting property in the multi-agent case, that players, to achieve this maximal value in this optimization problem needs to use a non-deterministic policy. Okay, so that's one critical piece that's different from reinforcement learning. In fact, a lot of the early reinforcement learning algorithms exploit the fact that there exists an optimal deterministic policy. Here, that's not the case. There are going to exist some games where you can't play with a deterministic policy, and therefore your optimization problem is going to be hard. Does that all make sense? Okay, I gave you one. Any questions? I felt like I went through that pretty quickly. Okay. Okay, so this, what I just told you about actually, is related, if not identical, to the minimax theorem, or it's a direct consequence of the minimax theorem. This is John von Neumann, and what the minimax theorem says in two-player zero-sum games. So two-player zero-sum games are a special case where I can formalize the problem of finding a policy as maximizing over my space of policies, such that I think you're minimizing over my utility function. And that's the same as if I try to minimize you maximizing against my policy. Sorry, the other way around. I always get that wrong. Player 2 is minimizing over their space of policies, assuming that I'm maximizing over mine. So it's kind of the same problem. We just switched the min and the max. These actually realize the same value. So V1 here and V1 there are equal. There's a lot of nice properties that come out of this. Okay, so it's a saddle point problem. The optima, these are these pi stars here. So optimal policies here. You'll see why it's known. We can think of it as an optimal policy. They exist. That's the first thing. That's really great. Historical note, by the way. This was in 1928. Nash's famous theorem only came in 1950. So this was proved 22 years before, which I always find a bit interesting. I think it's significantly easier, but it's funny that there was 22 years before it was generalized. Anyway, okay. This is called the minimax joint policy. In two-player zero-sum, they overlap with Nash equilibrium. So I normally use the term Nash equilibrium when I often mean minimax optimal joint policy. And here's the kicker. Okay, here's what makes all of the poker So I'm going to tell you a bit about poker AI later. This is the property that makes it all magic, right? Which actually comes back to the question you asked earlier. I can compute an equilibrium pi star, or a minimax optimal joint policy, and I can compute a different one, pi star prime. And now I can mix these two things, and I can get the same guarantee that I would get as if I was playing just one of them in isolation. So what does that let you do? That lets you design an algorithm that finds a pi star. It's centralized, right? So I'm looking at all the players' policies, I'm finding a pi star, but I only care about mine. I can take that one away, and I can go play in this game with somebody else, and if they're using an equilibrium that they use, computing their own algorithm, or using their own algorithm, and I can still get the guarantees that I would get if I was playing mine. That only exists in two-player zero-sum, but that's kind of why you can think of it as optimal, because I can pull out my own policy and I can still get the guarantee that I'll at least get a minimal value if I'm playing equilibrium. Okay. What it doesn't guarantee is that if I'm playing against a player that's suboptimal, making mistakes, for instance, I won't necessarily take advantage of that. right? But it's so in that sense, it's a safe solution concept. It's assuming that the other players are good or that they're in the space of minimax optimal joint policies. So it's really guarding against other players that are at least as good as me in terms of the optimal sense here. Okay, anyway, each policy is also a best response to each other. I spend a bit of time on this one because it's often not very highlighted, it's not very apparent that how much a lot of the work I've done relies on this fact. So I like to give it a bit, I like to appreciate it a bit.
Sorry, could I ask a question?
Yeah.
So when you say it's minimax optimal, is it a Nash?
So yeah, so this has been really important for a lot of the work that I've done in the past, this interchangeability property. Okay, any more questions about that stuff? Okay, so let me tell you a bit more about some of the algorithms in the space. So we looked at two actually. We looked at, I don't even know what that algorithm is called, iterating over the joint deterministic policies, and solving a two-player zero-sum game using linear programming. Here's another one, a classic learning algorithm called fictitious play. Fictitious play starts like this. Each player is going to be playing an average, it becomes an average policy. Each player starts with their own policy, completely arbitrarily, could be uniform random. And they're going to take turns. They're going to take turns finding best responses to each other's empirical average policy. So at the start, the empirical average policy is just the uniform random policy. So, and what they're going to do is they're going to iteratively add these best response policies to the set of things. And you're always going to be computing a best response to the average of all the best responses that you've seen from the other players. So maybe it sounds simple, but it takes a bit of terminology to understand. There's really two steps. You enumerate your best responses. So this, you can think of the initial policies here, gives you like a value. I'm going to compute a best response to this. I'm going to add it to my set. I'm going to compute a best response here to this one. I'll add it to my set. And then the next best response that player one computes is going to be a best response to the policy that you obtain by like uniformly mixing over these two. That's what I mean by empirical average. So the players maintain two things. They maintain their own average policy, and they compute a best response to the other player's average policy on each step. And once they've computed that best response, they fold it into their average. Yeah, so that's fictitious play. It was the simplest and first learning algorithm in the space, invented in the 1950s. It's had a lot of analysis. It is constrained, the convergence guarantees are constrained to certain classes of games, but luckily zero sum is one. Okay, but you might ask yourself, is this an efficient way of computing an equilibrium? Like, so here's an example. So we start with rock and rock. That gives you a value of 0 because they're tied. Sorry, this is in the game of rock, paper, scissors. So two players simultaneously choose rock, paper, scissors. Rock beats paper, paper beats rock, and scissors beats paper. So how would you learn this game? Rock, you can say, well, both players start with some arbitrary policy, rock. That gives both players a value of 0. What's the best response to that? Best response to that is paper. So both players are going to add paper to their set. And so now this is what I meant by the empirical frequency. You're going to be responding now. There are two strategies in your set. You're going to be responding. You're going to be computing a best response now to the mixture over these two things. So I'm going to play rock half the time, and I'm going to play paper half the time. And what would I do? I would add paper again, or maybe I would get a tie. And I could add paper again. And it's gonna. This is one of the problems with fictitious play. It's inefficient in the sense that it's adding paper an extra time, and you'll cycle through these. So now finally, because I have paper twice in my set of things, it now gives me, I now have enough incentive to add scissors to the set because we're more often playing paper than rock. Yeah, I went through that pretty fast. I hope that makes sense. But now it's like, think of this thing as a population where I'm uniformly mixing over these things. I still have paper as the most common thing, and the best response to paper is scissors, so I would add scissors. Okay, but look at what it was doing. It was generating, like the game itself only has it's only has 9 entries, but I've just generated a 5x5 matrix to be able to solve this. So is there a better way of doing this? Yes. There's something called double oracle, and maybe I've kind of motivated it through exactly how I was criticizing fictitious play. But what double oracle does, it basically starts with 2 policies, like arbitrary deterministic policies. So we'll do it again, rock and rock. Now we can think of this thing as a metagame. It's a different game that contains only 1 strategy each, rock and rock. But now I want to compute a best response to, like, I want to search my entire space of policies and compute a best response to the Nash equilibrium in this tiny game. So there's only 1 Nash equilibrium in this tiny game because there's only 1 action per player. Each player takes the action rock. That's the optimal policy. Very profound. Anyway, so what's the best response to the policy rock? Paper. So we're going to add paper to the set. So what double oracle does is it makes this game that grows by adding best responses that were from the original game. So you can think of this little thing as a tiny subgame that only contains rock and rock. I'm going to add paper to that set, but now I have a new game, right? This is the game that contains rock and paper. I can look for a Nash equilibrium in this game, right? Rather than just simply assuming that each player is going to be playing with a uniform policy, right? So if I look for a Nash equilibrium in this game, and then I compute our best response to that thing, I'm more likely to scissors, right? Scissors is actually the only thing left that I can add, right? So double oracle has the advantage that it's going to look through the set of deterministic policies that are left in the original game, and it's going to add one that you don't have currently in the set. So now we've expanded the game to its original size, and if we find a Nash equilibrium using linear programming, whatever, like we did before, that'll be the solution to the game. So that's double oracle. I may not have done it justice because I used the worst possible game for double oracle. So you might want to ask yourself, when does double oracle converge? It could actually require expanding the entire game, right? And that's the case in rock, paper, scissors. But the idea is that when you have large games, there's probably a small description of the set of over the set of policies or actions that you have that wouldn't require enumerating the entire game. And if you remember the definition of Nash equilibrium, the way that we were adding actions to the set of things is by looking for best responses. So if we can't actually find the best response to expand the game any larger, we've actually finished, right? We're done. We're at the definition of best response. Yeah.
Is there any robustness if you choose a different starting point? So if you iterated through and you haven't found the best response going through double oracle, if you choose a different starting point, would you still? It's not in the original set.
In the short answer, no. It's a very good catch. That's exactly one of the problems with double oracle, right? You could choose a bad order, in which case you enumerate the whole game by pure chance. If you choose the right order, you enumerate it in a very small space if the support of the equilibrium is small. I don't know of any work in that direction. I feel like it would be extremely relevant. So yeah, no, it's a good question. Anything else? So this idea of double oracle will actually become a little more relevant later. Okay, so I've told you a lot about zero-sum games. I've tried to motivate the optimization problem that underlies multi-agent RL in a very simple setting. So we've done zero-sum games. Let's take a look at cooperative games. So here's a cooperative game. And by cooperative, I just mean that each player has the same utility. So they're really trying to find utility that maximizes their value. Okay, so what would happen if we tried to do these Nash equilibrium algorithms here? Let's even just start with the first one. If we go to 0, 0 here, we can go one of two ways. We can go up. I mean, this player has incentive to go this way. This player has incentive to go that way. And then boom, we're at 2, 2. Everything around you is 0, 0. Remember the definition of Nash equilibrium is you only have incentive to deviate unilaterally, so all the other players are fixed. So when you're searching through this space of utilities, you either go up or down, left or right, but not diagonal. Right? So then you would find the Nash equilibrium 2, 2. So the question is that good? Here's the major problem. You see this 5, 5 here? I could have made that 10 to the 6, 10 to the 6. Then 2, 2 would be really bad. So the concept of Nash equilibrium is not really the right one here, because it is a fixed point in exactly the sense that it's defined, but it's very strongly conditioned on what the others are playing, right? You would want to be able to jump to the million, but at least if you're looking for a Nash, you could find one. You could end up at a fixed point that's arbitrarily bad. Okay, so that's just some motivation to say cooperative games are quite hard, actually. And then there's a class of games that's even harder. So here's a zero sum. Here's a general sum. So you can actually, there's no constraint on utilities. Right? That's the hardest. Okay. We've talked a lot about matrix games. Let's start moving to the sequential setting. We care about reinforcement learning in the end. Reinforcement learning is about sequential decision making. Okay, so here's one of these pieces of inconsistent terminology. In the game theory circles, they call this an extensive form game. You can think of an MDP as kind of an extensive form game if you made it finite. If you think of how to encode perfect information games, you can use this concept of an extensive form game. An extensive form game just really adds states to this whole thing. So tic-tac-toe has a number of states, and if you take an action, you go to the next state. Chess fits in this category, backgammon, Go, etc. And typically you define the utility only at the end of the game. In reinforcement learning, you're generally more you get rewards throughout the game. In the game setting, we normally think of just the reward at the end. So that's a model for perfect information games. So how would we formalize this if we were coming from the reinforcement learning world? We start off with a Markov decision process, which is just a bunch of nodes, and then you can take actions from each one of the nodes, and you have transition probabilities that get you from one node to the other once you've taken an action and a reward. And I'm actually going to enhance this by saying, okay, we want to be able to model turn-taking games. So I'm going to use this terminology here, tau of S. So S is going to be a state, which is basically just like the tic-tac-toe board. And tau of S is just going to be the player to play at S. And we're also, and I think this is unfortunate. I didn't mean to use the same letter here. We're also going to enhance the player set with the special player called the simultaneous move player. And what this tau of S function is going to do is going to identify who's to play at that board state. So tau of S for the initial board in tic-tac-toe would be 0 or 1, depending how you're encoding your player numbers. Okay. So we can define the rewards per player. So that's kind of new. So normally in MVPs, you see like a reward of R from going from state S, A to state S prime. Now there's more than one agent. So now this reward, you can think of it as a vector really, but each player is going to get a reward for all the players in your set. And you can actually define the returns that you would see in reinforcement learning. So this thing is a return. It's really just like the collection of rewards that you see throughout your experience. And you can also index that thing with the player, because each player is going to get a separate return. Okay? So really that's just enhancing an MDP to make it into kind of a perfect information. Okay, so I've talked a bit about some game theory, and now we're going to move up into like the crux of multi-agent RL. Once I give you the description of an extensive form game that I just gave you, let's constrain ourselves to the perfect information world. So we're trying to learn how to play tic-tac-toe, right? We're going to be doing a lot of that today. But this is actually not tic-tac-toe, but it could be a sequential game where there's 5 things, depending on whether you count terminals. That's not for now. It's going to look like this. We're going to be almost exclusively dealing with game trees, by the way. So a game will not have cycles in it. That's an important distinction from MDPs. If you want to know the reason, just come ask me. And here's what it looks like. Player 1's going to play. They can go left or right. Player 2 then plays. They can go left or right. Player 2 plays here. They get player 1 gets a 4. Player 2 gets a -4. So this is actually a zero-sum game because all the utilities sum to 0. How do you solve this game? Like, what does it even mean? Is there a Nash equilibrium in this game? Like the concept of Nash equilibrium, does it make sense in these extensive forms? Actually, let's start from the start. Like, what does a minimax optimal mean? How would you apply the idea of minimax optimal to this game? Yeah.
One way to do it would be to like start at the bottom of the tree.
Yeah.
And just look at for player 1, what is the best choice he can make from that spot.
Yeah,
Right?
exactly. So
And then player 2 can assume he's going to make that choice
Right.
if they go to that node.
Nice. So let's do that. And let's add a bit of terminology while we're doing it. So let's take this thing, this little portion of the game, we're going to call that thing a subthing. It might not be obvious right now, but in this class of games, that is a well-defined game on its own. Maybe that is obvious. That will become subtle in later this afternoon. But this thing is a subgame, so it's a well-defined game on its own. Player 1, what does player 1 want to do? They want to take the right action because they get +6, and player 2 gets -6. So that's good. We've solved that subgame. Okay, if we solve that subgame, player 1 gets 6 to -6. Let's just keep going. Right? We'll solve the subgame too. Why not? Okay, good. So player 2 wants to get -2 because it's higher than that. Okay. Okay, so you can actually do exactly what you said. We can now think of this thing as a leaf for a terminal, right? Because we've solved it. Player 1 is playing optimally in that game. So now we can go back, and that's exactly why this is called backward induction. You basically just go back up the tree and you would just do this. Okay. Player 2 gets 4 -4 because they choose this branch, and you just go up and boom. Okay, so then we've solved the entire game. This player is going to get 4 -4 because the optimal path is this. Also called principal resolution. Okay, so that's how you solve perfect information. This you would see in a game theory textbook, like the one I showed you earlier, the Multi-Agent RL textbook. The RL people would not call this backward induction. They call it value iteration. Actually, it's not quite the same thing, but I'm going to draw a parallel between the two worlds. Okay, so if you read the RL book, you're going to, let's go back. I'll even go more general. I will call this approximate dynamic program. That's a bit of a lie. It's not approximate. It's really just dynamic program. But we can do it in an approximate way. And that's what value iteration is. So value iteration is like the first thing that you see in the reinforcement learning textbook as a way to solve Markov decision processes. Think of Markov decision processes as a slightly more general model than perfect information games, except perfect information games comes with the fact that like it comes in the multi-agent stuff. Now, value iteration is intended to solve is an algorithm to solve MVPs. MVPs are not multi-agent, right? But I'm told you I'm going to try and make a relationship between these two things. And here's how you do it. So let's just think about the single agent setting for now. I'm solving a Markov decision process. So like maybe an agent is trying to find its way in a grid world or something. Here's what you can do. You can actually assign a value function. This is going to be interesting. This is going to be important. V of S is a value function. It's really like, think of that as how good the agent thinks of this state. The agent, is this a good state or is this a bad state? We can initialize the value function to be 0 everywhere. And we can do the following. We can just sweep over the state space. So look at all the states, and we can ask ourselves, well, I can look at my value function of my next states, and I can just choose the best one. And I'm just going to keep doing it. I'm going to add a reward because, of course, the Markov decision process has a reward, and I'm going to estimate my value function by just basically doing like approximate dynamic. This will converge by induction, and this is one of the sort of the basic algorithms in reinforcement. Okay, so that's value iteration. I'm going to turn it into backward induction or approximate backward induction, and it's beautiful how easy this is. So this is the first thing that's going to connect our two worlds. So the player to player S, we've agreed that's going to be tau of S. And the reward to player I is Ri. And because we're dealing with a case of games, there's a subtlety here. We're going to say that the actions that a player can take is in the set of legal actions. So it's not going to be, your action set is not going to be consistent across states because you're playing games. And just to make things easy, we're going to assume gamma is 1 if you know what that means. Just, yeah, it's irrelevant for now. I mean, it's a detail. And here's how we're going to augment the values of the states. We're going to, if I sum over all the states, is under some threshold. But my value function, all it did was change by being indexed by the player. And that's it. You just change a bunch of these things to be indexed by the player. So this, I think, is beautiful, really. And it's beautiful. I mean, this is exactly what AlphaZero is doing, right? Like you can do value iteration or policy iteration in zero-sum games. And actually, zero-sum games in the perfect information setting are no harder than single agent. Because you can make this assumption that you can break down the game in these sub games, and then you just maximize the value over your subgames. Okay, the only thing that's changed is that the interpretation of the values are different. You have to make sure that you're maximizing your own value and that you're flipping the rewards depending on who's playing. Yeah. You have a question?
Sorry, can you reiterate the difference from rewards and value?
Yeah, so the reward. Okay, yeah. So the rewards are like per state rewards. So like a reward, if I go from state S, take action A and get to state S prime, I would get a reward normally. So in the single agent setting, that would just be given to the single agent. And I'm just extending that by saying there's a reward given to each player. So in tic-tac-toe, let's take tic-tac-toe. The rewards would only be given at the terminal states, and it's for whoever wins. So the winner would get a +1, loser would get a -1, and the rewards are 0 everywhere else. Does that make sense? And the values are just estimates. Those are like the agents are building those. So these values are just, they start off at 0 for every state in your game. And the algorithm is actually just computing. So you're updating, it's like a table of values.
But isn't that the thing you want to maximize?
That's right. Yeah, exactly.
It gives the total score, basically.
It's exactly the expected, yeah, you want to interpret it as the expected value as of the policy that I've computed through iterating over all these size. So it's really just doing backward induction, right? Like you go back to backward induction. It's doing it in a approximate way because the ordering is not the same ordering as top to bottom necessarily. Like you're just sweeping over the space and you're just doing these backups, these value backups. And the value, this V of S that we're talking about, is really just this, right? That's it. So that's really nice. And you know, I mean, this is maybe obvious to some people, and they're not nearly as excited about it as I am. And the reason I'm excited about it is because it's the first in the line of things that connects like game theory to reinforcement in the multiplication case. Okay, so this is also known as minimax, by the way. So the minimax algorithm, that like one of the classic ones we learn in artificial intelligence, almost always looks like a search algorithm. And it's really just backward induction. Backward induction applied on the entire game is just minimax applied on the entire game. And normally, when minimax is taught, you assume this like heuristic value function, right? And that just falls out of the sky. Like we know something about our game, so we're going to say, you know, like peace ranks in chess or something. So we design a heuristic evaluation function, and you go in and you implement minimax search, and that's just a depth-limited search that's essentially doing backward induction over this heuristic function. So here's one of the reasons I find it so exciting, because this I've related value iteration in zero sum to just the standard value iteration. You don't have to stop there. You can just do it with policy iteration, and essentially that's what alpha zero does. So it's going to compute a set of values using deep learning. It's going to improve the policy by doing these Monte Carlo tree searches, and it's going to train a new policy using deep learning. Okay, so I've talked a lot about turn-taking games. You don't have to stop there. You can actually you can do this with simultaneous move games. Simultaneous move games, you can think of them as basically just matrix games, where when you take an action, you don't get a utility, but you get transported to a new state, where you all just act simultaneously. So how would you solve these? You can use backward induction again. It's beautiful. So if you go through here, you look at this this value here, this state. You can encapsulate this state piece for leafs, so that's the end of the game. You can summarize this state with this matrix game. And so the value that you send back up would be the value attained by what you want to be able to do here is a max, just like we were doing before. You can't quite do a max, but you could do a min-max and use like linear programming like we saw earlier. So this actually, these simultaneous move games were one of the default, or still one of the core formalisms that are used by the multi-agent reinforcement learning community in the first set of papers. And they looked at like little tiny grid soccer games here. And one of the earliest algorithms is essentially just doing a form of value iteration in two-player zero-sum simultaneous move games. So like this max operator that I told you about, you can't quite do that when you're choosing simultaneously, because you're maximizing over what? You have to maximize assuming that your opponent's not. But I told you how to solve this problem earlier, right? You just use linear programming, and you can define your value functions like this. You have the problem, of course, that you might need a stochastic policy because of the game that we saw earlier, like matching pennies. But okay, the nice thing is the values are still, because of the minimax theorem, the values are still unique, which means if you solve this optimization problem and you send a value back up, that thing will converge to a fixed value. Okay, so this is really the first algorithm. It's called, it extends Q learning to the minimax case. It extends Q learning to the case of simultaneous move games. So if you know Q learning, you maintain these set of values, very similar to the value function I showed you a second ago, but they're Q values, which are normally state action values. You're going to augment that representation with the opponent action. So this thing induces a matrix of values like the one I showed you before. So the Q value is now really indexed by state and all of the player's actions. In the two-player case, it's just a matrix. So we can define the policy as in value iteration. And we actually sample through the game. We generate trajectories through the game. And we basically maintain estimates of these values. And what we send upwards, like what we say is our max over the future states, we need linear programming to be able to solve. Okay, but it's really value iteration with like you're sampling through the state space to collect data. It's not that difficult. Okay, so let me tell you that was the first major algorithm in multi-agent RL. It was like 1994 by Michael Littman. Largely responsible for at least my excitement in multi-agent RL. There were, at the same time, so now I'm going to go through more history than algorithms. Well, I mean, I'll cover algorithms, but not in much depth. So the first era of multi-agent RL had actually two branches to it. And it's the same branch of value-based RL versus policy grading. So in the first branch, like this minimax Q algorithm actually had a strong effect on the excitement in this field. So people went off and said, hey, we need to generalize this outside of zero sum. So we're going to look at how to do it in general sum games, how to do it, how to learn correlated equilibria with all kinds of things. We're going to learn how to do function approximation with it. So this is really the first era of RL. The other branch was looking at, can we do policy grading like algorithms in this scheme? So this is one of the first ones that I know about. And this literature has a lot of these kind of diagrams in it, which is really trying to understand, if I define like a differential equation that says, move my policy in a direction of greater value, what do the vector fields look like in the case of two-player games? And they try to, now you can use tools from nonlinear dynamics, but to say, my system is either chaotic, or not chaotic, but stable or unstable, depending on what the values look like. And here's how we can expect that players are going to change their policies, and you can characterize them using like these phase portraits. So like a lot of the literature just contains this idea of here's what your system looks like if your utilities look this way. Here's what you can expect is going to happen if you use policy grading. And, it's unfortunate that there's some games where the equilibrium point is in the middle, and your policy gradient just kind of like cycles around it. Right?
What was the name of that paper that you had on the previous slide?
This one? Yeah, IGA actually. If you look up Singh and IGA, that's like one of the main papers in this that started out this field. This like sort of policy gradient direction of multi-agent RL. My supervisor actually worked on a major algorithm in that space called Wolf, Winner Learn Fast, which you'll see in a few minutes. Incoming, so the evolutionary game theory people come into this setting in an interesting way. So if you know anything about evolutionary game theory, there is this policy, essentially it's the field of evolutionary game theory is kind of inspired by survival of the fittest, population dynamics, and one very specific learning algorithm is the replicator dynamic. The replicator dynamic is roughly inspired by trying to increase the proportion of individuals in your population that have better fitness. So you can look at it this way. I can describe that in the form of a differential equation by saying I'm going to change my policy over time. So this is just a time derivative in a way that weights it by my own policy. And it's a function of if I were to use if I keep the policy of the population fixed, but I change to use action A more often, how well would I do compared to the actual population average? Right? That gives you this kind of gives you an idea like, well, if I switch to action A, but everybody else stays the same, I can expect to gain such and such. And the differential equation is just modeled around. That's called the replicator dynamic. It's pretty much central, or it's like the first dynamic you learned about in evolutionary game theory. It's all related. like to this first era of multi-agent RL, because a lot of these policy gradient papers were looking exactly at these phase portraits and trying to characterize them, and evolutionary gradient theory was already doing it. So here's some of the cool, really kind of neat ones. So you can define. There's a really nice survey paper by Carl Swills and colleagues of mine that I'm working with now, actually, that really summarizes a lot of this work. So first era of MARL, here's this algorithm I mentioned before, Wolf. One of the ideas, winner learn fast, was to try and characterize, again, like certain notions of like properties that we want in our algorithms. So rational would be one of them. If the opponents are fixed, we would like that our learning algorithm actually just converges to the best response. That should be a basic thing we should expect. And we're going to call that rational. Convergent is we can guarantee that our policies will converge. What this work did was showed that using a variable learning rate was important to convergence in 2x2 games. So here's just another list of papers. Like, yeah.
Can you give any intuition about why that might help?
The variable learning rate.
Yeah.
Yeah. So it's like think of it as a. I want to tell the story, but I don't think I'll do it any justice. So I'm going to just tell you a little bit. My supervisor called it the mama bear and papa bear. The idea, I don't know, I don't remember the story, but the reason behind that. But the main idea is because one player is learning slowly. Like, let's say there's two players. I'm learning faster than you. You're moving your policy slow enough so that when I go faster, I'm learning a best response to your slow moving policy. So it's like I can catch up to you in some sense. That's always the intuition that I've had behind it, but I'm not sure exactly if that's the right answer.
So the variable rates are between players, not about like at a step in the algorithm.
No, it's definitely a step in the algorithm. That's the intuition behind why. I think the variable learning rates in multi-agent reinforcement are good because if you have players moving at the same speeds, like, okay, let's here, I'll try and explain it. I'll try to explain my intuition behind this in the picture. If you look at a game like rock, paper, scissors, and both players are using policy grades, and they're both acting with a similar learning rate, you'll get this circle. How do you change that? You just make the gradient one less than the other. And the reason is now you're gonna go this way. Now you go one of two ways. You can go outside, right? Or you can go inside. Because you're forcing the players to learn at different rates. And so my supervisor's thesis actually had a lot of these diagrams where, so he formalized this, right? I'm only giving you the intuition. But he formalized this to say, if you're using such and such learning, if players are using learning rates of this form, that you can guarantee that you're going to converge in certain classes. And it's for this exact reason that you're not like you're not just going around this circle only because you're using the same learning rate.
Is there any value to switching which player learns faster or slower?
Yes. Okay. It's a function, if I believe, this is going way back, so I might not be able to answer it, but it's a function of how close they are to an equilibrium. And you need the equilibrium policy of the other player to determine what the right learning rate is. That was one of the major restrictions. I could be getting this slightly wrong, so please double check these facts. But yeah, good questions. Okay, so I only have 12 minutes before we should break for lunch, so I'm going to zip through this last bit. So why call it? So there's two parts left.
I have a question on the last
Yeah.
one. Should I wait till later or?
No.
So it's about the like the alpha zero algorithm.
Sure.
And so like for deterministic policies, the true value of the state of a pair of deterministic policies is 1 or -1 or 0.
In a game where the rewards are 1 - 1 0. Yeah.
Right.
Yeah.
But that's not what like the value estimate will be for. And that's because you're doing this kind of like tree search, approximate tree search. But I still only have like a hazy interpretation of like what those numbers mean. Can you say something about? Like, the
Oh, yeah, okay.
interpretation of-
So the value function. So AlphaZero is learning two things. It's learning a policy, and it's learning a value function. So and they're both mappings from the input, which is roughly the state. The value function, you should really interpret it in the same way that I've been talking about. So it's really like if both players use the joint policies, this is what my expected outcome will be. Now there could be stochasticity in the domain. If there is, then that might be it might not be 1 minus 1 or 0. Right. But there could also be capacity problems with your function approximator that's not going to give you exactly the values 1 minus 1 or 0. But the way you should interpret that value is if I start at this state and I play according to the policies that I'm generating, that's an expectation of what that value will get. That's what you're trying to estimate. And that's exactly how you actually train these things. You look at the outcome of the game and you just build a regressor that tries to predict it. So I don't know if I answered your question.
Yeah, I think so.
Yeah. Okay.
Yeah. It's hard for me to. It's not intuitive because the expectations are actually deterministic, right? Like for pair deterministic policies.
So the policies are not necessarily deterministic.
Okay.
And so the way that actually that's kind of interesting. That's one interesting element of AlphaZero. The way it teaches the way it learns its policy is it does a Monte Carlo tree search, and it tries to match the policy to the distribution over the visit counts. So let's say you have 3 or 4 actions that are giving you the same value. In the Monte Carlo tree search, those actions might have been taken at roughly the same proportion. Your policy is going to actually be a stochastic one over those values.
Okay.
Now that's it doesn't have to be that, because in the classic games like we applied it to, you could just choose one and for it to be and maximize that one. That's fine. The reason that thing is good is because you're still exploring between those options. Like you haven't really truly discovered which one is the best one.
Right.
But it's like roughly looking all good. So it's like I'm going to play in proportion to like what my Monte Carlo tree search tells me at the end of my search. So the stochastic, the policies that we learn are actually stochastic. And we've looked at them too, like in Go, even in Go, they're stochastic. Actually in Go, one of the big reasons like the policy net was really helpful was that the branching factor is just crazy. It's 300 and something. I feel like 60, was it 19 by 19? 361. You can't afford to search all those actions at each one of the states. So the policy net was really filtering them all out. Right? But over the ones that it determined were good, it was claiming some stochastic policy between them. So the expectation was over a stochastic policy.
Okay.
Yeah. Even if it wasn't, no, that's wrong. Sorry, I was going to say something. Did I answer the question though?
Yeah.
Okay, so I keep calling this the first era of multi-agent RL. The reason I call it that is because scalability was a major problem. So they were working on all kinds of nice formalisms, showing all kinds of nice theory, and everything worked on 2x2 matrix games, or simple grid row games or something without function approximation. Okay, today we have the inverse problem. So come in 2015 around 2015, income deep learning meets multi-agent RL. So we've discovered this new thing. So this all sort of like kind of the excitement in multi-agent RL kind of died like around 2006. Yeah, sorry.
I was curious about the question for scalability. What would be your sense for what is a large multi-agent system? Given like current, I guess maybe like.
Okay. It depends how you define large.
Previous examples, like you were saying, small matrix games. So then saying, great scalability, what's the problem? I'm imagining, what's the size of the system or how many agents in the system? Till we say that's large, or till we say that's.
No, that's a very good question. So I mean, I can give you my answer to that, but if you ask somebody else, it'll be different. 2x2 matrix games are definitely too small. No, I know that's obvious. I'm just saying, like that's absolutely. We can start there, right? So this matrix soccer game would have been great. I think, like Lippmann's original paper here, I kind of like that because Minimax 2 was trying to get out of this like 2x2 matrix game like setting. What proved to be hard, like this work was done entirely in tabular. What proved to be hard was actually doing function approximation in the way that RL algorithms normally do. So I would be happy if we can even get up to, something like this little soccer game. If I were to go back to 2000. And around 2004, it was like one of the first papers that wrote Lagudakis and Parr here, L2 actually, showed how you could do linear function approximation in this set. And that was nice. But nothing much happened after that for some reason. Okay, but your question was about what do we call big? My answer to that is I care a lot about the foundations and about the sort of the guarantees of your algorithms. Sure. So for me, Texas Hold'em is already big. I think that's actually Texas Hold'em is still pretty big, even the limit version of Texas Hold'em. So it's a really hard question to answer because I can answer it in many ways. We're stuck on two agents. We have to get rid of that, right? But it's way harder than it sounds. We're also stuck on the size of the domains. So we've been using Leduc Poker as an example of a domain that has 1,000 states. So that's not large in terms of number of states, but the complexity it adds to the algorithms is not representative when you just take a look at the actual number of states and compare it. For me, Go was huge, right? Same thing with shogi and chess. To be able to do that entirely without human knowledge, so that's definitely in the class of big. But it's perfect information, and it's two players, right? So it's exactly. There's so many axes I can tell you that I want to move, and probably if I were to give anybody some advice, is pick one of them. Find an interesting problem where you can escape those restrictions in just one of those. Because if you try to do them all, it'll be really too hard. Even if we can start, so StarCraft, right, is really, really, really big. It's really impressive, right? Especially the complexity of the problem is just insane. And it's still two players. So there's so many axes that we can play with.
2 players, 0 sum.
It's 2 players. So it's defining big and hard is not easy on its own. I really like diplomacy. So diplomacy is a nice 7-player game because it's actually 0 sum, right? It's not 2 players. That would be that's very large. And there's some exciting results that came out of Facebook recently about trying to do just supervised learning on a human data set, for example. That's a very long answer to your question.
No,
sorry.
That's perfect. At least I think that when I try and meet papers and say, great, I want to look for something that's scalable. Let's say I want to run something we go over to agent-based modeling land where say I'm going to start with fixed policy agents that never learn anything, and we scale them up the size of the city, then they're expensive. Versus scenarios where you were saying, I'm gonna look at 2 or 3 player games. State space is so massive now; it's very expensive. I was curious, just more about your sense of how you're, thinking of scalability. That helped.
Yeah, no, that's. I think we're still in the world so. And the other thing I'll say, because it's really relevant to me, it's are you willing to give up the guarantees of the algorithms? If the answer is yes, then do whatever you want, right? If the answer is no, you unfortunately have to stay in small games and kind of because the priorities are different, right? I want to know if this algorithm converges, so I'm going to prove something about it. But then I'm going to run it on a game where it can actually test the empirical convergence to Nash, right? I can only do that on Leduc-sized games. So the kind of thing I usually work on is I come up with algorithms that have nice properties, I think anyway, and then I test them in games that are small enough to test them. And then I test them in a very large, hopefully, game where I don't know what's going to happen, but hopefully something good.
I have a follow-up question. So from your point of view, if you have just one axis along which we've made most progress for the sense of scalability of optimizing the agents, which axis would you say, or maybe would you say we made the most progress?
Where are we along which axis have we made the most progress?
Yeah,
So if I had to choose scale as an axis, that would be one. I didn't when I was working on AlphaGo, I didn't realize how quickly we would be able to get so good at Go. So what were the ingredients for the success there? One, like the algorithm itself. I like to think about my reaction to the algorithm when it was first told to me. Right? It's like, of course that's going to work. It was just, why haven't we done this yet? Like, this is, of course. So the scalability, like why were we able to scale there? Because there were large improvements in supervised learning that we can kind of import. It's like, residual networks. So that's kind of convenient. I think this will work in games. Boom. Multiple policy, like mixing the policy head and the value head. Just deep learning was just like that. That's exactly what characterizes this second wave, right? Is we're going to pull out like a lot of the stuff that has worked in the single agent setting and use it in the multi-agent setting. So that's the first one. And I think I'm going to use Auth0 again to say the search. Like Monte Carlo tree search was working really well on its own. It had not been combined with deep learning up until that point. If you look at, for example, capture the flag is another success of multi-agent reinforcement learning. This is like, again, the reinforcement learning algorithms were getting really good, and the models were getting really good. And now you can apply it in games. That's an example of scale. Capture the flag is a very good example of how we've gotten out of two-player zero-sum, because it's like, it's a cooperative game and a competitive game at the same time. The Hanabi challenge, which I'm going to mention in a few minutes, is another one where we've gone out of two players. But we're still just making little bits of progress there. Perfect information versus imperfect information. AlphaStar is a great first example of that. Pluribus, all the work on poker, like the Alberta work, I've been a part of this also. It was still very much, two-player zero-sum up until Pluribus, right? But the same thing with DeepStack. So DeepStack is another algorithm where there was, they finally learned how to do, to bring in deep learning that they didn't do before. So I think it's really like, if I characterize it, it's really like the stuff that's buying us all the scalability is really is really enhancing our algorithm, and that's where we're succeeding most right now. And the only thing I don't want to do is sacrifice. Like, I don't want to build algorithms that are not from the ground up. That's sort of like my take. So so there's a lot of these independent learning approaches that we're taking. Now I'm just going to do a very quick survey of like, the second era of multi-agent RL. So people were basically taking a lot of these new techniques, like DQN, for example, right? You can make it multi-agent. You can even use Atari, right? So you can make Pong multi-agent. Now each one of them, there's one agent that controls each one of the paddles. You can learn to communicate. That's something that's really been exciting over the last few years. Agents, you can put agents into environments where they have to communicate with each other, and now they have. You can impose this as an independent learning problem, and there's a lot of success there. Partly again through this deep learning meets multi-agent RL. Now you can actually come up with architectures that are relevant to the problem you're studying, right? Cooperative multi-agent tasks such as StarCraft, right? This is one of the interesting ones. I really like this video because two agents are trying to catch this blue agent here. And really this is just entirely driven by independent reinforcement learning algorithms. Each one of those is using an RL algorithm, and you define the rewards in a way. In this particular instance of the problem, the agents actually get higher reward if they catch them together. So that's why you see them hesitating sometimes and like waiting for the other agent. But I think this is what this video captures. I think what I really find interesting about multi-agent RL. We just put a bunch of DQN agents together. We define rewards in the environment, and look at this thing go. This is what comes out of it. Yeah, so you have like a lot of different. So if you have a cooperative problem, you can actually use this idea of centralized critic, which computes a value function that's shared by all the agents, and they're each independently learning a policy. AlphaGo. We talked a lot about AlphaGo. Like this is just amazing. Like, I mean, the first AlphaGo had. Yeah. Did you have a question?
Sorry.
Oh, sorry. Had human knowledge. Then like we sort of just took out the human knowledge. I largely believe that wasn't going to be possible. They proved me wrong. Then we went to 3 different games using the same algorithm, same hyperparameters. There was a lot of excitement when you combine, reinforcement learning and multi-agent reinforcement learning with these new, deep networks. And so there's just a lot of people doing all this work again. Here's something like a multi-sumo, I think it's called, where you have agents trying to push each other off this platform. You have spiders that are playing soccer, right? There's so much work now that's being done here. Capture the flag that I mentioned earlier. Agents are actually, like when you watch these videos, it's just amazing. Like the agents are actually capturing the flag. They're cooperating with humans. So it's easy to see why people are getting excited by this. It's OpenAI 5. OpenAI played against humans in a competition. Same thing with AlphaStar. So that's just really the cap on. I just went through like a quick survey of all the interesting results or papers. There's this nice survey I like to point people to if you're interested in multi-agent RL. It was recently accepted as a journal, actually. Yeah. Sorry.
I was just wondering, do you see curiosity-driven learning applicable to these or the next step in some of the future research that you're?
I think curiosity-driven learning really affects. It's like I think it affects everything, not just multi-agent. I can't say anything about it in the multi-agent setting, in particular, except for the fact that, like in the multi-agent setting, you have this joint exploration problem, which is you can't just think of exploration. Like exploration is a big problem in RL. Now you can't just think of it in isolation, because my values are going to depend on how we're jointly exploring. So we need an idea of what curiosity means in the case of multiple agents, right? Like, do I condition my curiosity or my sort of exploration on how you're exploring or how you're acting? Can we jointly be curious? What does that even mean? So I can only relate it to the problem of exploration, which is even harder in multi-agent, if that makes sense.
Is it okay if I ask a left field question?
All questions are welcome.
So, I think this is very, very fascinating, elegant stuff. I'm trying to think about applications to human endeavors where there's a lot more stochastic. So, for example, one would be, are there people that looked at this to help teams play better in sports, in real sports, with the greater stochasticity.
Right.
And I was also thinking that this could affect things like drug discovery, where you create a molecule and you look at it as a game, like is it soluble, is it going to be toxic? And then the other idea of multi-agent was some of our efforts in the scope of the health are directed at trying to look at social media and see if we can sort of go against some of the trends that are not good health suggestions that people are taking up and just agreeing with.
Yeah.
And so we want to look at influencing when there's agents that are antagonistic who don't necessarily know their motives.
Right.
Nash equilibrium doesn't necessarily apply because you don't know all their motives. They have to learn that a little bit.
Right.
I mean, you want to you have a strategy, you have a goal that you want to achieve, but you've got these agents more or less are interfering with your plan. You have to kind of counter their efforts.
Yeah, so I have an answer that could turn into a very long one. So I'll give you a very short one, and let's talk about it at lunch. So there were 3 kind of questions in there. One was, like you have stochastic domains that are maybe more representative of like real problems. I will make mention of a project that my supervisor had, where he was actually working on the idea of curling, very Canadian, even though he's American. And he was actually working with the curling club in Edmonton. So he got really interested in curling because of like there's something that was bothering him that was unknown about how the physics of a curling rock on the actual like ice. And he said like he found an actual paper on this, and he went and read it, and he said, "Oh my goodness, we have the model."
We have a curling player.
Oh, nice. So he developed an actual Kuhn that you could play against and say, "Oh, this is a curling situation. Like, what should I do?" And he had some AI in the background that said, "Oh, if you do this and you act in such and such a way, you can expect to win this many times." He was actually partnered up with curling. That was before this whole deep learning era. So I don't know exactly. I'll point you to some literature. That's the first question. Second question, I forgot what it was, but I had an answer to.
It was loaded. I was just looking at different places where with greater stochasticity and uncertainty, you don't necessarily know the rules, you just have goals.
Right.
And you have state measurements.
Right.
And you have agents kind of working together. And the developing chemical.
Oh,
you can construct. What I'm trying to say is, I think you can construct it as a multi-agent problem and be able to make progress on developing.
Right. So I have a very similar answer, which is you're absolutely right, actually. And it turns out that Abe Heifetz, who's from the University of Toronto, actually did that. And now he works for a drug discovery company. I think he founded his own unit. So he came to me when I was at Toronto and actually pitched something very concrete. And he went off and did it after, so that I can at least point you to one paper where they formalized it for the game. And they used proof number search, which is like a solution concept, like an algorithm, perfect information base, to find new drug, to synthesize new drug. That's about all I know in that space, but I found it very interesting.
Yeah.
And I really want more. I want to find more examples of using games, game theory, and AI for something that's not related to like
right. And the third question is
decision.
about social media.
And social media, yeah. So the quick answer to that one is, this is actually a fairly big field now in multi-agent RL. So there's a lot of papers that are coming out of the conferences in multi-agent learning about like influence graphs and like the idea of like how the networks of information spread and affect people. I don't know how relevant it is to like kind of fixing the fake news problem or the kind of like antagonistic spread of bad knowledge. Yeah, exactly. I don't know how close we've gotten to solving some of those problems, but I can at least tell you that people.
No.
Sorry that I don't have a better answer.
No.
Okay. We should eat at some point, and I'm gone over, so I will just finish this last part. This was really, I only had a few slides left over here, which I might mostly skip. I think I want to show you this one thing. This is something I discovered this is something I worked on with collaborators. Because, and there's a bit of a backstory here. So one thing so I told you a bunch of the successes of all these applications of reinforcement learning in multi-agent RL and why it's easy to get excited. I was cautious about this excitement. And the reason I was because I knew that we're going to get into trouble if we use this idea of independent reinforcement learning has a gotcha. So, and here's what it is. So like, let's look at, actually, I'm just going to describe it through videos. Okay. So the first video on the left are two independent learners that learned together. So as you can see, they're like sort of well coordinated. So each one of these independent learners, again, this was partial observability, so I'm showing you the entire map that they had with small viewports, so they can actually coordinate despite that. Their viewports were very big, so they can almost see. And when you play them again together, they do sort of what you expect. They find each other, they tag each other. That's how they get rewarded. Okay, so each one of the players here learn their policy through independent reinforcement learning. And what I mean by that is they were applying a reinforcement learning algorithm blindly without knowing that they were in a qualification set. They were just getting rewards from somewhere. Okay. The problem with that is that their environment is non-stationary. So the environment is changing as a function of how you're acting. Because if I'm going to go tag you, you're going to move somewhere else. What that means is that your experience that you're generating, you're going to fit a policy to it, expecting that your environment is going to act in a particular way. So what we did was we said, okay, we're gonna do 2 experiments. In experiment 1, it's going to be identical to this. 2 players are independently using DQN. In the second experiment, 2 players are also using independent DQN. And the only difference between this first experiment and second experiment was that they used a different random seed. The same algorithm. It's a 5x5 grid world, right? And what we did was we took policy 1, so the blue player's policy 1 from experiment 1, and the red player policy 2, and we let them act against each other. And here's what we found. They would do this. So what's happening here? They're not generalizing at all. This is scary, right? They're using the same algorithm, the same environment. The only thing that's different about the 2 things is that they use the different random seeds. So they're generating different kinds of experience. They're fitting their policies on what they expect the environment is going to look like. The problem is that strongly depends on what the other players are doing. So you're very strongly overfitting to your training data, right? What we noticed was, as we make the environment larger, these are the agents that learn together, right? There you go, nicely coordinated. And the same thing happens over here. And we actually quantified this problem, and we showed that it got worse as you increase the domain and as you increase the amount of partial observability. So look at this. And so you can quantify this by saying, okay, if I do this experiment, I can measure the amount of rewards they get. I mean, this is scary. Look how small the domains are, and this is happening. So yeah, this was. I'll finish up with PSRO because essentially that was the idea behind PSRO, which is an algorithm that is inspired by these reinforcement learning algorithms for imperfect information games. So how do you get out of this? You get out of this. Well, okay. Here's one way to get out of it that's inspired by game theory. Playing, for example, on a game of poker, and basically what you do is you just simulate. Now that you've sampled a policy, you simulate how well that policy does against the other policy that you brought. Then you get like this small matrix, which has one action, one policy, right? So that's how well, if random plays against random, it'll get 0.5. And what's cool about this is you can go back now and you can say, well, the idea of computing a best response, you can consider that, like we saw earlier, that is a single agent problem when you fix all of the opponents, right? So the idea is that I can fix this opponent to be random. And I can use reinforcement learning in the way it's intended. It's a single agent problem now. I could just use DeepRL. So I can have a DQN agent that's learning a best response to random. So I'm going to add that to my set. I'm going to add a DQN agent to my set of policies. And ideally, you just grow the set like you did before in double row. But now you're doing it on a metagame, right? This metagame is the matrix game that summarizes the entire game. So here's your first best response to random. This one's the best response to random. But now how do these do against each other? Okay, well, this thing is kind of like an empirical game, we call it, which is just like a small version of what my metagame. It's a metagame essentially, right? It's a metagame where I'm going to restrict each agent to choosing to play the best response that they generated. I can find a Nash equilibrium of this thing, and then I can play. I can just keep adding oracles, and I freeze them once they're done training, and I just keep going. Okay. Yeah. So that's I think where I should end. So the PSR was very much inspired by this idea of double oracle, but what gets us to scale, so it's part of the answer before, is now we have DeepRL. DeepRL is finding the best response because it's a single agent problem and it's doing exactly what reinforcement learning is meant to do with all the power of DeepRL. So this actually inspired the AlphaStar League. I was super happy to find that out because I felt for a long time that real-time strategy games were kind of like this big rock paper scissors game, but in like meta space. So it was really cool to see that. Okay, we'll stop here for lunch. I had a bit extra on this section, but I think I'll kind of fold it. Yeah, thanks for listening to me give you a very high-level overview of Monte Carlo in that first session. I know there's a lot of information to throw at you in a very high level and very quickly. So this time, what we're going to do is we're going to look at two specific problems. Sorry, we're going to do two examples, and we're going to kind of work it out. So the first, oh, thank you so much. First thing you have to do is watch me drink coffee. Oh, yeah. After lunch is really like when I need coffee the most, right? So you don't want me to collapse. Okay. Okay. So the second session is going to be a bit more like practical in a sense. We're going to actually work on real problems, small instances of them. I want to get you. I mainly want to get you interested in the kinds of problems of adapting reinforcement learning algorithms to zero-sum games. I've chosen a few things I want to highlight. So here's the plan. So some worked out examples, adapting Q-learning to two-player zero-sum games of perfect information, and an example of something of an algorithm that has been quite popular in the poker AI literature called counterfactual randomization. So when I was designing this session, I thought, well, other than some broad high-level overview of multi-agent RL, what would I like you all to leave with? Well, like, what are the most important things that are teachable in 2 hours, or whatever time we have to take away from this? And so I went back and thought through my whole research career, and these are the 3 things. So I'm going to give you a small snippet of like the things I think that I've worked on, which are the most, or at least the things I'm mostly interested in. So to be able to cover these require a bit of depth. There's a bunch of notation, and I actually want you to understand this stuff. So before we get there, we're going to work on two examples together of like little exercise. Okay. So to do that, you're going to need this handout that I sent around. I only printed out 30 copies of it, so you might have to share with your neighbor. But yeah, here are the 2 examples. So we're going to go through a detailed example of CFR. Like we're actually going to run the algorithm, compute the quantities. If you have any, if you know about reinforcement learning and the kind of quantities that you maintain in the algorithms, it's going to be interesting to see how they're different in the CFR world. But before we get there, we're going to actually just step out of our. We're going to start with the basic Q-learning algorithm and try to see how to adapt it to the 2-player zero-sum case in the perfect information zone. Okay. So I promised you, by the way, I would tell you the result of the game. I think there's only one person. The average was 23. I'm very happy the average was 23. 23 is actually a nice number for me. It's my birthday and my wife's birthday both fall on the 23rd. So 2/3 of that is 15, and there was only one guess. So is the person who guessed that still around? Still? Very good. You're the winner, my friend. You win nothing. Sorry. I didn't bring anything. But very good. You played the game very well. You secretly know what everybody was going to guess.
That's just my favorite number.
It's also the optimal policy. So using this as reference, let's do a dive into two examples, and we're going to run tabular Q learning in two different concepts, contexts. Okay, so refer to this handout and basically try to answer question 1. Now I've talked to a few of you. I know that you all have different backgrounds, so I think for some of you this question is going to be extremely easy. And for people who haven't seen reinforcement learning, this question might be new to them. Drawn a node up here because chance actually has states to act from, right? So that's chance's node that was not there before. So this is a path from action A. From node A, I'm going to take action A. I'm going to get to node F. At node F, I'm going to take outcome 1 because I rolled the dice and it landed on a 1 or something. I'll hit node B and I'll hit action C. That's called a terminal history because it's a history of the playing of the game that gets to a terminal state. Okay, here's another terminal history. Okay, in fact, there's 8 of them. Here is a history. So when I call it a history, it's a non-terminal history. So taking action A, and then followed by outcome 2. That's just a partial history. The only reason to think of these two things differently the thing that unites these two ideas is that a history always starts from the start of the game. Okay? But histories can be prefixes of each other. And there's a special set of terminal histories that refer to the entire playing of the game. Okay, so far so good. That's pretty basic stuff. I'm just giving you some definitions. Here's a really cool one. Here's another MDP. You start at node A. Actually, there's only one node. You can take action E that gets you 0. You could take action P, and with some probability you're gonna like 0.01. You're gonna get the value of 100, and with a 99% chance, you're just gonna get the value minus 0.05, and you're gonna return back to the start. Okay. Now notice this is an MDP, so you actually can have cycles. A game tree does not have cycles. So I'm going to try to define an important notion called perfect recall by telling you that I can think of this MDP in a different way. So I can think of this MDP as basically just an infinite number of states where at this state I decide whether I take E and end the game, or I take action P and I land either in this other state, or I get a reward of 0 and the game ends. And then I can do that again. Then I can do that again, and again, and again. Now, these are equivalent, as long as this can be infinite, right? There's one major difference with how we're going to view states that is really relevant to this example. Okay, does anybody know the Markov property? If I say the Markov property, can you tell me what that is? Somebody volunteer to say that.
Probably make the transition to the next stage in the history.
Right, exactly. The consequence of that is how I act over here is completely independent on how many times I've pulled this lever and tried to get the 100. It doesn't matter. I can define an optimal policy if I've done it 1,000 times or if I've done it once. The observations on this side are going to be slightly different because node A, the optimal policy is going to be the same, but node A, whether you've reached node A or node B or node C, are completely different game states, right? This distinction might seem strange now. It's going to be very important when we kind of talk about imperfect information. And this idea of perfect recall. So perfect recall is essentially just a property that states that the agent never forgets the observations it receives throughout the game. So what this means, I use this example to illustrate. If I've taken the action P 17 times, that's a different state for the agent than if I've taken the action P 16 times. Now, it just so happens that in MDPs, you don't need to make that distinction. In imperfect information games, we're going to have to make that distinction. So the Markov, actually, the perfect recall is an analog to the Markov property that we're going to need in our set. And all it means is that during an episode, I'm not going to forget like these sequences of times that I've actually landed in different states or in the same state. Okay, so that's what I mean by perfect recall. That's going to be very important. Okay, now a bit of context on what this CFR algorithm is. So counterfactual threat minimization was invented at U of A by Marty Zinkovich and colleagues. The University of Alberta Poker Group was hugely successful in computer poker. The main idea, up until a few years ago actually, was to take an original game, like as large as Texas Hold'em, that couldn't fit into memory. So we couldn't do anything like value iteration because it was just too big, right? You take an abstraction algorithm, so you group states together that are similar, you define an abstracted game, but it's still a well-defined game, and then you apply this Nash equilibrium solving algorithm that we're going to actually talk a lot about. You find a Nash equilibrium in this smaller game, and then you reverse back. You get a policy in that abstract game, and you reverse back and you use that in the full game. This was actually the formula behind like one of the major successful Texas Hold'em results in 2008, where they played against human professionals and won for the first time at heads-up limit. It was the algorithm here that was used to solve the games between the abstracted game and the Nash equilibrium. This is where CFR sits. So this abstraction mechanism here was based on human knowledge of poker. So you know, A7 and A6 are roughly the same like buckets of cards. Like you say, you have very, very similar winning chances from those two hands. So we're just going to put them together and call it the same state, right? So you lose a bit of precision there, but that's how you can get the game down to a manageable size. Okay. So what's really important, and what I'm really fascinated and interested in, is that this algorithm CFR will not look like reinforcement learning, but I'm going to make the analogies to reinforcement learning as much as I can because that's what I'm currently excited about. Okay, so let's talk about a very simple game, Kuhn poker. Kuhn poker is a simplified poker game. There's a 3-card deck, and player starts with 2 chips, and they start the game anteing 1 chip each. So they put 1 chip into the pot, so they only have 1 chip left, and they have 2 actions. You can pass or you can bet. So you can think of a pass as a fold, or a call, like bet on the phase. So if the first player bets and the second player passes, that's a fold. The second player folding. If the first player bets, the second player bets, that's a call. But you only have 1 chip, so you can only. It's really, really simple. 26 games. The reason I'm using this game is to tell you what a state is. Okay. So here's what the game actually looks like. There's a chance node at the top. There's 1 chance node. Think of this as the shuffling of the deck. Each player gets a single card that's face down. So there's 6 permutations of permutations of cards and the way they can be dealt. There's 1 left out. And we group together the ones that are consistent with our observations. So if I get, so think of this game state here as like a world state, right? That's the state of the world where player 1 got the queen, player 2 got the jack. This is the state of the world where player 1 got the queen and player 2 got the king. Right? So with respect to player 1, these are kind of the same states. We kind of put them together. And we're going to call that being an information state. Right? So we're going to look for policies that map information states to actions, so distribution poker actions. Okay. So I have a few more slides to describe this concept. It's really important that you understand this, otherwise the next half an hour is going to be completely confusing.
So maybe I just don't understand this game quite as much, but like say if you look at the very leftmost 2 node, how can or rather, like calling and folding have a reward of 2 and 1? Just like this. So like, is that you bet 1 and then they raise the 2, and then if you fold, if they fold, you lose 1 or gain 1.
Yeah, so you're anting. Oh, sorry. So the utility at the end is the difference in the money. So I started out with 2 chips. I put in 1 chip and I have 1 chip left. So here's what happens. I've been dealt a queen and I bet. That just means raise, essentially.
Yeah.
So I put in another chip. Now, if you call, I've won because in this branch you got the jack. That's why it's a utility of 2 for me, right?
Sure.
Now, if you fold, then I just win 1 chip because I was lucky enough to get the queen. Because you didn't call, so you didn't put any more money into the pot. So I just got the the chip that you bet originally.
But why does, instead of betting, passing also lead to 2? Like, maybe it's not.
Oh, sorry. This is player 2's nodes, right? This is not a utility.
Oh, okay.
Oh, sorry. Yeah, this just
Yeah,
means player 2's turn.
Got it.
Yeah.
Sure. Yeah, that makes sense. Got it.
Yeah. So then, if you pass, if you both pass, I still win because I have queen. If I pass and you bet, then I win more from you again. If I call, because I have the queen and you have the jack.
Sure. Yeah.
All makes sense?
Yeah.
Okay. So it's definitely keep asking those questions because this concept you will not understand anything for the next half an hour if you don't understand what this means. I'll go through another example. So an information state, S, corresponds to a sequence of observations with respect to the player to play at S. So let's go out of Kuhn poker now. We're in a bigger poker game. So we ante 1 chip per player. I maybe still get only 1 card. So that's my observation. And the sequence of actions that we've taken up into that game, the sequence of actions that all the players have taken. We group all this thing together. We call this the information state. The only thing that's missing is the private observations of the opponent. Right? So I want to look at my state. I want to look at my information state. And this is where, this is one of the purposes of perfect recall, is that you remember everything that happened. So I remember that I anteed 1 chip. I remember I got the queen. I remember that I bet, and I remember that you called. All that together, we're going to put all that together. We're going to say that's an information state. I'm going to map my policy. That I'm going to act from there, right? But it's not the same thing as a world state, because a world state would actually contain the private cards of the other player. But it is an information state is formally a set, and that's why some people also call it information set. It's a set of the world states that you could get, right? So this is just like, I want to act from this point, but I could be in one of many worlds. But my policy is going to act the same way because I can't condition on stuff that I don't. Okay, so we're going to go into a little more detail on information states, but that's the main idea. It's really just a state with respect to what you know. Okay, the environment is in one of many world states. I keep using this name world state. What I actually mean is histories. So the world state, if we go back to our MVP example, every world state is a 1-to-1 correspondence between a world state and a history, right? That's exactly why I told you to think of chance as a picked player, because it's under that condition I can say every history is a world state, because you start from, because those histories include the outcomes that chance decided. Okay, so I'm going to use this terminology a lot, H in S. So this just means like the world states that are in the information state. So far, so good? Okay, so a full history of actions, including natures. Okay, let's go back to our friends von Neumann and Nash. In 2-player zero sum, we saw this earlier. We're looking for these kind of policies that have this property. In the extensive form case, so in the case of sequential games, it's the same thing. We're in the 2-player zero sum case. We saw this earlier. I'm just going to restate it because it's going to be important. This is what we're looking for, these operations here. So we're still looking for Nash equilibria, right? It's just the Nash equilibria are a bit more complicated in this case. The policies are functions of states. right? So you have, just like in reinforcement, you have state action policies. At each state, you can decide, I'm going to play with certain actions. You're going to mix over your actions. You can, it's possible that you need stochastic policies to be optimal. Okay, for the same reason that we needed it in the case of matrix games. Okay, so nothing has changed. The only thing is I'm saying this is a function of the states as well, the policies. Okay, we're ready to almost describe CFR. This is how I see CFR. Counterfactual regret minimization is policy iteration. So it's actually not quite policy iteration. It's going to be a variant of policy iteration. It's going to be related to policy iteration. What do I mean by policy iteration? I mean, all players are going to be playing with the policy. And we're going to compute some values, and we're going to modify those policies based on those values. That's what generalized policy iteration is in reinforcement learning. And CFR is actually that, with a slightly different way of, a slightly different interpretation of policy iteration. Okay, but it follows the same rough formula, which is that we're going to evaluate each policy to compute values, and we're going to use those values to improve the policy. Okay, it's not quite policy iteration in the standard way of thinking, so it's a special kind of policy iteration. I'm going to tell you about these things called counterfactual values. That's going to be important to what I'm going to talk about. And we're going to improve the policy in a slightly different way than you would do in reinforcement. But for example, just using and there's going to be this nasty piece to it, which is that to compute something that's optimal, we're going to actually have to compute this average joint policy. That's something we didn't really need in the standard reinforcement. Okay, so that's an extra piece. Okay, so on the very high level, that's what's different about it. Now we're going to go through each one of these pieces. Oh, sorry. The first thing I should tell you is that because the CFR theorem, that was one of the biggest things that CFR brought to the table, is that you can do this, this step 2 here. You can do that by doing regret minimization locally at each state, rather than just globally. That's what CFR is actually fine. So this improvement, this policy improvement operator, you can define a notion of regret at each information state, and you can change your policies locally, and then you're actually just minimizing regret in the full game with a rate of 1 over t. So, yeah.
What's t?
Oh, sorry. T would be like the number of iterations. Oh. Okay, so this is an iteration algorithm. So you run it for a number of time steps, and the epsilon Nash, the epsilon in an epsilon Nash is basically just like the way that you approximate Nash equation. Epsilon Nash just means if I deviate to a best response, I can gain, like my opponents can gain at most epsilon. Okay. Oh yeah, I had that. Okay, here's Kuhn poker again. This is a nice visualization. I have to give all the credit to Daniel Hennis in the OpenSpiel team, also in Paris. He actually wrote this visualizer that takes any one of our games that we have implemented in OpenSpiel and visualizes it. It's really beautiful. Anyway, okay, so this is back to Kuhn poker. What we're going to do now, through an example, is I'm going to actually run CFR only on this state here. Okay. So what is that state? That's a state. Let me tell you a bit about this encoding, which is maybe not as obvious. 2B, that is a key for the information state. What that means is I've gotten the king. So the actual cards here are 0, 1, 2. What this means is I've gotten the king. And the current betting sequence is my opponent bet. My opponent actually put a chip in. That's what this information is. I can get there. The reason there's 2 of them is because I got the king, and my opponent could have gotten the queen or the jack. Okay. So, yeah, sorry, I should also mention these utilities are in view of player 1. Right? So clearly, if you get the king, you want to bet. So this -2 is actually, like, think of it as a +2 because this is -2 for the player 1, but we're trying to think of what player 2 would do. So you definitely want to bet because you would get more. So player 2 is betting. They have an inferior card. You know that because you have a king. You definitely want to bet here. Okay. If you pass, that's actually wrong because you have the king, and you're basically just giving them a chip. Okay. So how does CFR discover this? Let's go through it. Let's compute the values for the statement for this thing. Now here's where this thing will come in handy. So if you look at the handout on the other side, there's a bunch of notation, and I'm going to go through each one of those things. Define what that Q value is. Okay, so let's do that before we start with the example. Okay. Before we even look at this, I want you to think of this thing in the same way as we thought about it. Oh no, over here. It is trying to roughly represent the same thing. Okay, so on a high level, this is a value. It's an expected value starting from state S, taking action A, following pi, and that value is with respect to player pi. Okay, it's a slightly different notion of value, and that difference is going to be important for some of the things we're going to play with. Okay, for now. I'm just going to put the superscript C there to say this is a counterfactual value. Okay? All right. What are these? What are each of these pieces? Okay. This history H and this history Z are basically like all the histories, all the histories in this information space S paired up with the terminal histories that you would reach if you played starting from H, right? So maybe I can graphically depict that because it might be easier to show, or it might be easier to think about what that thing is. So write some information space. In the case of Kuhn poker, you're going to have 2 of them that you can be in. And Z of SA is going to be all the possible terminals that you can reach if you had started from here and you took action A. Okay, so this is what Z of SA is. Just like the pairing of each one of these, like H and H prime. Okay. And this is actually looks like a monster, but it's not that complicated. This is a utility. It's just a utility with respect to player pi. Okay. So these things are reach probabilities. These ADAs. Okay. Let's start with the right one. This is a reach probability, and what I mean by reach probability is just like a product of probabilities of the policies. That from of the path that starts from H and gets to Z. Okay, so I wish I could draw on this, but I can't. This guy is just an expected value, right? It's really just an expected value of playing with the policy, starting at H, going to Z, over all the Zs, and the Hs, and the utility. Okay, so far so good, right? So that's how you just compute an expectation in the game tree. Okay. This is the magical the piece. Okay, this is a reach probability, but it's a reach probability of only the opponent's policy up to history H. Okay, that's why we call this the counterfactual. This is a counterfactual value because you're thinking of what the opponents could have played up to this particular point. The policy might be stochastic. So your value function is exactly the same as your Q value function, except you sum over each one of the actions that you can take, and you multiply by the Q value So you're basically, this is just over your time, over your 2 values. Okay, so let's start. We've got 2 histories in this state here, and the histories look like this. Player one got the queen. Player 2 got the king, and there's been a bet. Okay, that's 1, 2, and E. The other history is player 1 got the jack, which is 0. Player 2 got the king, and there's been a bet. Okay. So the reason that we're collapsing the information state is represented as 2B, because this initial chance node is the card that player 1 got. So player 1 is in blue, by the way. Player 2 is in red. Does this notation make sense? I know it's a little cryptic.
Can you say it one more time?
Yeah, sure, no problem. So I wish I could write on this again. Okay, these are the 2 histories we're looking at. This one is H, and here's why it's H. It's player 1 got the queen, that's deal 1. Player 2 got the king, and there's been a bet. Player 1 got the queen, player 2 got the king, and there's been a bet. That's H. That's the left one. The other one is player 1. No, we have to get there this way. Player 1 got the jack, player 2 got the king, and there's been a bet. Okay? Those are the 2 histories, and we're collapsing these 2 together because from the perspective of player 2, they don't know what player 1 is. Okay, so now we're going to compute this guy, which is the counterfactual value of state S, the counterfactual value of playing action P, which is pass, in state S, and we're going to just compute those. We're going to compute those things that I told you about earlier. Okay, so let's go back. If you look at the handout, the sum contains 3 things. So this is the first part of the sum. So where's this 1/12 coming in? This 1/12 is 1/3. That's the probability of this of the queen. Then 1/2. You multiply those together. That's 1/6, right? And then here you get 1/2 again, because there's only 2 actions to take, and those are all opponents. See what I did there? The MVP. When I told you to think of the MVP as a multi-agent system, the opponent, you always treat the chance player as an opponent, a fixed opponent, right? So that's where the 1/12 comes in. That's that counterfactual reach that I was talking about. So this is like the probability of the opponent's actions to get to that point. Okay? The 1/12. Now we have to compute the rest of the expectation, which is quite easy. From here, it's 1/2 because we're using a uniform. Oh, I didn't tell you that. Everybody starts with a uniform pulse. So the players are playing with. They're playing with the take action bet with half and action pass with half. Okay, so that's the second part of this sum is the 1/2, and then a -1. The reason it's a -1, remember, these are in view of player 1. So you need to take the utility in view of player 2. So this is actually a -1. Okay. We're not done with the sum. We have to keep going. Does that all make sense, first of all? It's like we're not done with the sum, but that's the first thing we've summed over. There's only one more thing to sum over, because the Z of SA here is just these 2 things. Sorry. This one and this one. You have to take pass in both. Okay. Now, it turns out the other one is exactly the same. You take 1/3, 1/2, 1/2, that's 1/12, 1/2 again, and you get a -1. Okay? So that's what the counterfactual value for passing is with respect to those policies and those actions. Okay? So let's do the other side. What's the counterfactual value for betting? Well, the 1/12 hasn't changed, right? The counterfactual reach probability here is the same as the last time because we're getting to the same place. That's good. 1/12. This is also hasn't changed because we haven't changed. We haven't updated our policy. The only thing that has changed is now we get a utility of 2, right? So betting with the king is good because you want the king. You have the king. You want to win. So you get 2, and it's going to be exactly the same on the other side. Okay. So we sum these 2 things and get 1/6. Is that clear so far? I've never gone through CFR in such detail. The first time I did it, but I really like this idea of Kuhn poker. It's like small enough to be able to show you exactly what CFR is doing, focusing on one information state. Okay, here's the value of the state. So this is the value of each, the counterfactual value of each action given the policies. Here's the value of the state. So the state is just a weighted sum of each one of these values, weighted by the policy. I told you the policy is uniform, so it's going to be 1/2 times minus 1/2, 1/12, plus 1/2 times 1/6. Which is just over 0. It's actually 1/24. So you can think of this thing as, again, this would be the counterfactual value. If you start from state S, and all players are playing high, and the fact that it's not quite an RL value, or it's not quite the same as an expected value, because it's weighted by this counterfactual thing. And this relationship will get very interesting. Okay? Now, you might be asking, what do you do with these? Like, once I've computed these values, now what? Here's where the regret comes in. Okay? So this, now what you want to do is you want to compute the regret. And here's how you want to interpret these things. You can look at each of these values and you can say, well, I could decide to change my policy. And how would I change it? I would change it by choosing action P, right? If I stick with my uniform policy, this is what I would get. And actually 124, because I'm mixing equally over these 2 things. If I change to action P, I would get this. If I change to action B, I would get this. And I kind of look at like what my baseline value is. My baseline value is I'm getting 1/24 if I stick with my policy, right? So what do I prefer to do? I don't want to stick with my policy. I want to change to B because I'm going to get 1/6, right? Now let's quantify that, how much I want to change. So that's a regret. So the regret of starting from state S, taking action P, is just this, you just subtract these 2 quantities, right? If I were to switch to action P, this is how much I would get. If I stick with my policy, this is how much I get. It's roughly minus 3/24. So I don't have any regret. In fact, I have negative regret. The way you want to interpret this regret is regret of not changing to the false. So negative regret is actually bad. I don't want to do that. Positive regret means I have regret over sticking, like if I were to stick with my current policy, I regret not changing to action B by 3/24. Okay. Now, that's the notion of counterfactual values. The whole algorithm is based on this. I've pretty much described to you 90% of the algorithm. Now what you have to do is you take these quantities and you decide what you do with them. And really all you do is you tabulate them. So you actually have a table that stores the cumulative regrets, and you update your policy in a way that's on the handout, which is the first sheet. So you take your regret values and you look at the positive portions of them and you normalize over the positive portions of the regret. So it's really easy to do over here. This is a negative regret. The positive, if you apply this plus operator, this thing goes down to 0, right? You only look at the regrets that are positive, and then you normalize them. Well, there's only 2 actions. One of them is negative, that's going to be a sign of probability of 0. One of them is positive, that's going to be a sign of probability of 1. So that's how you change your policy. Okay? That magical last step there, that's called regret matching. And it's an algorithm that's been associated with CFR from the start. Does it all make sense so far? We've only done it for one information state. The CFR algorithm goes through all of them and changes the policy all at the same time. Okay, so that's CFR operating in Kuhn. Any questions on the computation of the values? Was anything unclear? Was it too long and explicit? No? Okay. Okay. Here's the exercise. It's much easier than Kuhn. Okay. Here's a variant of rock, paper, scissors, where it's called biased rock, paper, scissors. We're going to assume that this utility is a 2. So this is a 2, this is a -2. That's the matrix game version of it. Here's an extensive form version. There's an equivalent game of rock, paper, scissors where I write down on a piece of paper what I play, rock, paper, or scissors, and then I'm going to put it face down. And then the second player does the same thing. Okay? I want you to think of rock, paper, scissors in that way. That's roughly what this game is. Player 1 writes rock, paper, or scissors, puts it down. Now that becomes an information state because the other player doesn't know what they chose, right? So the state of the world could be in one of 3 different things. Either the first player wrote rock, wrote paper, or wrote scissors. And then the second player chooses rock, paper, or scissors. And this is the utility that the first player gets. If that happens. You're all happy because we learned something new. I want to tell you a bit more about these values. So this is a counterfactual Q value, that's what I'm going to call it. It's still conditioned on the joint policy. It's still a return or some version of the return to player I. So it looks a lot like the Q values that were maintained in the tic-tac-toe example and the V values that we maintained there. The only difference was this C, okay, where we weight by the opponent's probability. Okay, it turns out there's actually a formal relationship between an expected return that you would use in the algorithm in reinforcement learning and these values. And I'm really excited about that because then it gives you a link between these 2 worlds. In particular, you can look at RL algorithms that compute these quantities, the RL quantities, and you could say, because there's a formal relationship between these 2 things, when you go to apply the RL algorithms in the 2-player zero-sum games, you can get convergence guarantees that you didn't know about before. Okay, so we're going to go through this derivation, and actually part of you working out the whole CFR example was for you to understand exactly what this notation is. And this is going to be like an embarrassingly simple derivation, but I'm super excited about it. Okay, so here we go. What's a Q value? So I want you to think of a Q value as an expected return starting from state S, playing action A, and then following pi. Now I kind of told you to think of a counterfactual value that way, but here's how a Q value is actually different. So a Q value is trying to compute this quantity here. Let me explain it in a diagram. Okay, you start at the state S. You have a distribution here, a proper distribution. So this is some uniform. This is not necessarily uniform. This is some probability distribution. And the way that you understand what this value is representing is it's really representing this expectation. So I'm drawing in blue. If I wanted to compute this expectation exactly, here's what I would do. I would say this is some probability, and this thing is an expected value. It's an expected value weighted by the reach probabilities, starting from here to get to the bottom, multiplied by the utilities. Then it's weighted by this probability here, and we do that for all the hidden states, and we get a value. Okay? So this is kind of like the standard interpretation of a Q value. Notice I did not draw the C. So this is not a counterfactual value. This is just an RL style Q value. The only thing that's different than like the standard setting is that this is a partially observable game, which means you could be in one of these states and you don't really know which one you're in. But there is some underlying distribution that is a function of the player's policies that determines which one of those they are. So I can, if I know both players' policies or all players' policies, I can compute that thing, right? All right, what is a counterfactual value. Okay, so you all just computed counterfactual values. So I think you know what it is, but I'm going to give you a slightly different way of thinking about it. So, you know how we weighted everything by this eta minus I? One way you can interpret that is it's a value, oops, it's a value. This was the second part of the term that you used, right? You were actually computing an expected value. This is eta h z times utility of z for each one of these, for each action. So far, so good. Here's what's different. You actually didn't have necessarily a probability distribution here. You actually had just the counterfactual reach probabilities, right? Which is these things, right? The reason it's only a green for, like it's not green here is because that's the same player to act from state S. So it's like you don't consider these because you're saying, oh, this player is trying to get to this information state. Therefore, they're going to change their probability here to 1. So I don't want to include that in the weight. Okay? It's not quite, so this thing is not a probability distribution. These are just weights, right? One way you could see this value is that you're conditioning not on starting at state S. It's actually an expected value of the root state. It's the portion of the expected value under S, given that player, this player to play at S is trying to get there, meaning every time they have a chance, they choose the action that would lead to this state. Okay, that's actually a lot to wrap in your head. I appreciate that. It's maybe a bit of a contrived version of value. But if you want to understand, if you want to really think about what is this thing representing, it's not quite as clear as the standard thing. Okay, but now we're going to get from one to the other. So we're going to define this thing, Q values of SA, to be the expectation of some trajectory that's sampled from the policy of the return, conditioned on the fact that we're starting at state ST and we're going to take action. So this is right out of the reinforcement learning book. I just said it in words. So let's just keep going. Now we're going to use some of our notation. So in a game tree, we can state this as, this is that bottom part of the expectation, right? That's similar to what you just computed with CFR. This is that distribution I told you about. So the probability of being in state of world state H, given that you're in information state, ST. Okay? And we're going to sum over all of the terminal histories that go through S and take action. Okay? So the only thing that's different, right, is this term is the probability of being in state H given state ST. That is going to be a probability distribution. Okay, so far so good. Let's expand this. So how do you, now we're going to apply Bayes' rule. And that's like literally the only step of like ingenuity that you can do. So we're gonna restate probability of H given ST times probability of H divided by probability of ST. Okay, so this is well defined. What's the probability of reaching ST given both players' policies? We can compute that thing. What's this? This might not be obvious. Anybody want to venture a guess? Like, we know what the quantity is. We know what the value is. So remember that, oh, maybe you don't remember. H is in ST. That's exactly what this thing means. Probability H, like H is actually, the state S is defined by the set of H's, such that H is in S. So this is 1. Probability that you reach state S under history H is 1. The reason for that, this is where perfect recall comes in. You don't have multiple histories getting to the same state. So this thing, you know that you're in state S if you reach history H. Cool, so we can take that out. Okay, and oh yeah, and H, sorry, this should be H is an ST, and H is unique ST. Okay, well these are kind of quantities, these are actually, now we can expand just by definition. Boom. So this is the probability that you reach state H It's just the reach probability starting from the start state. That's what eta is. This thing is just the probability of reaching S of t. You just sum over all the different h's. Okay. I lied. There's a slight bit of engineering here. So now you can pull this apart into player i's reach probability and player minus i's reach probability. So all I've done is taken this term, split it into the two players' different contributions. Okay? Okay. Now here's what's cool. I can pull this guy out of this sum. Okay, so now that's maybe not obvious. Here's how you want to think about this. So what have we done? We've taken, let's go back a step. The probability of H divided by the probability of ST. All we've done is expand that into reach probabilities, expressions of reach probabilities. We've split this up into each player's contribution to those reach probabilities. Okay, so this reach probability includes all players. This reach probability includes all players. That's, you could just separate them, it's no problem. So now this is player i's and player i's. Okay, I told you about this magical property of perfect recall. Perfect recall states that for each history inside of an information state, the only thing that's different about each of those histories is what the player doesn't know, right? So if I look at an information state, it's composed it's composed of a set of histories where the only thing that's different between these histories is things that I don't know. Okay. Now, what is this reach probability? This reach probability is just a product of my own policy's probabilities of all the states that I saw along this history page. It has to be the case that I could never have distinguished each one of those histories along all of the states that I visited, because I never found out what the opponent had. That's exactly that. I'm using imperfect recall there, right? So this guy is the same no matter what H, no matter what world state. It didn't matter what card you had. I played the exact same way along this history because I didn't know you had the jack. I also didn't know you had the king, right? So if I look at all the sequences, I couldn't have played any differently because the sequences are only different in the private information that I didn't know about. Okay? I don't know if that's clear, but all that means is that if I'm summing over the histories in that state, this is the same for all of them, so I can pull it out. Okay? And that's because that's the use of perfect recall. That's it. This thing now cancels with that. Boom. And we have this beast. And just because I like summarizing this and introducing more notation, actually, no, I'm not get there yet. Okay, so it might not be clear to you yet, but this thing is, well, actually, no, it should be clear to you because you just computed all this. That's a counterfactual value. Cool. So what does that mean? We can actually take that, and this thing is a counterfactual value. So all we did was do one base normalization step. We took the counterfactual reaches, and we said they define the probability distribution using Bayes' rule. We said the counterfactual Q values are related to the RL Q values in exactly this way. And I just call it, in my papers, I just call it this because this is a Bayes normalizer. Okay? I'm super excited about it. Now, here's why. Okay, so it's a very simple derivation. It was kind of already known. It wasn't really just explicitly written anywhere. Here's what excites me about all this. You can now go to the reinforcement learning world, and you can say, what is a policy gradient algorithm? So if you look at, so this might not be familiar to you if you don't know policy gradient. This is called an all actions policy gradient algorithm. It's essentially like you're defining a gradient over some parameters theta. The idea is that theta parameterizes your actual policy. So this is a gradient. You're trying to move, you're using basically gradient descent to move your policy in the direction of higher reward. So you take the gradient of your policy with respect to those parameters, and you multiply it by the difference in the Q value for taking state action SA and the actual baseline, which is normally just V of S, but you can think of it as the sum, the weighted sum of the Q values. So this is just standard stuff, right? There's nothing new yet. What's really exciting though is that through this relationship that I just told you about, we can turn these things into counterfactual values. And the only thing that's actually different is that they end up being divided by this multiplied by the spatial normalizer term. Okay. So why that actually matters is that we can make a relationship between what policy gradient is actually doing without talking everything at all. Like just standard policy gradient. We can say if you run it in two-player zero-sum games, you can get some kind of convergence guarantees because we're going to import a lot of the CFR theory. We're only going to be able to do that through this relationship. Okay. So we have a paper on this. It's called, if you want to look it up, it's regret policy gradient. I think what's really cool about one thing we did in that paper is we changed the standard optimization problem that underlies policy gradient by saying instead of doing hill climbing on some value function, you can actually do regret minimization. So you can interpret, so what this policy gradient that you saw a second ago, that's still doing, is trying to maximize the value, the notion of value, right? But what's really cool about that paper, I think, another thing is you can really think of an advantage. This thing is also called an advantage. It's really just an immediate regret in the same way that CFR calls it regret. They're literally the same things. So if you're in the two-player zero-sum setting, you could say, hey, I want to change my optimization problem to minimize regret instead of maximize value. If I do that, I want to interpret this thing as a loss, like as an error function. And I want to do gradient descent instead of gradient ascent, right? And we put this little plus because we don't care, like for the same reason as before, we don't actually care about like negative regrets. You're never going to play them. So we want to get to a region where we're actually like this quantity is 0. And you can take the derivative with respect to these function approximators and then just do gradient descent. And the whole interpretation, like the whole idea behind this is I want to compute a policy such that at every state, I have no regret playing with my current policy. If you've done that, you've reached the Nash equilibrium. That's the definition of Nash. Okay, so but now you could do it with function approximation. That's what wasn't easy before. As I told you before, in the CFR world, what we used to do was we used expert knowledge to create expert abstractions, and then you would just apply CFR as a policy iteration. But that expert abstractions trick always felt like unsatisfying, right? But now you can actually just do, you can throw deep nets with, zero knowledge and just learn. So that's cool. So that was one of the papers I'm really excited about in one of the relationships. I'll tell you a bit more about this one. I'll go through this one relatively quickly. There's two things I think that distinguish RL algorithms from like the computational game theory algorithm, like CFR. You just ran CFR unbiased rock paper scissors. Most people you talk to from the reinforcement learning world are going to say that's not an RL because, like Q-learning, you didn't actually sample, right? We go back to the very first graphic that we saw. An RL agent is essentially experiencing the world by taking actions and seeing observations, like sampling experience from the world, and then learning from it. Right? You didn't sample experience from the world, you ran over the entire game tree, right? That's what separates policy iteration from reinforcement. Okay? I'm telling you all this because basically my thesis was about Monte Carlo CFR. So Monte Carlo CFR, the idea behind it is really simple, right? We're just going to add sampling to the mix. So instead of computing these quantities by visiting the entire game tree, we're going to sample portions of the game tree. We're going to estimate these quantities using estimators, using the portion of the game tree that we sampled. We're still going to improve the policy in the same way using the graph matching, but we're going to maintain estimated average joint policies and estimated regrets, estimated everything essentially, right? And the whole reason it works is because we can do this in an unbiased way. Okay. So I'll go through this one fast. It's actually, the proof in this case is really actually much simpler. And I'll just give you mostly the intuition. So let's say you have a game tree and terminal histories. We're going to define these blocks. So these are just like, think of them as subsets of the terminal histories. QJ. So QJ is a subset of all the terminal histories. It's important also that all the QJs, all these blocks, when you take the union over all of them, it spans the entire space of terminal histories. Okay. And we're going to compute these estimated quantities. And the estimated quantities are only going to be computed for the states that we actually get. Okay. So yeah, that's it. So they're estimated given the block that we have. Okay. And then we're just going to use estimated regrets based on these estimates, and we're just going to update our table in the exact same way using the estimates. Okay. All right. So let's define this little QJ to mean the probability that we sample QJ. QZ, I want you to interpret that as the probability of sampling any terminal history Z. So that's going to depend on which blocks you sampled. So it's going to, for every time Z appears in a block, you have to add those up. So that's the probability of sampling Z. A particular terminal history. So let's consider state S that has 3 actions. We can define H to be a prefix. So H is a prefix of Z using this notation here. Z of S is has the same interpretation as you had before. It's essentially all the terminal histories that start from S, so that have H as a prefix. And here's the messy definition of a counterfactual value. I've sampled counterfactual value. So all these quantities you're familiar with because of the exercise. And we got this kind of beastly thing here. So let's just interpret what that is. So the counterfactual value of starting in state S following pi is an estimate. You sum over the 8 for all the histories in the state. That was just like before. So this was good. Well, what you did before was H is any Z of SA. Now the only difference you're going to do is you're going to intersect. You're going to make sure that the terminal history intersects the block that you sampled, and the terminal history is reachable from S. That's the only thing that's different. What that does is it introduces a probability of sampling that terminal history, and you divide that probability. Does this look familiar to anybody? So this is actually just importance set. So this is called an importance sampling correction. You've sampled this terminal history Z, you divide by the probability of having sampled it. And what does that let you do? It basically lets you have an unbiased, it's essentially a definition of an unbiased estimator for this quantity. So I'll show you how we get there. So this is what we want. So this is like one of the main things from my thesis. I was really excited when my supervisor showed me this. And the one thing I didn't realize is that this is exactly off policy Monte Carlo. So I think that's one of the things that got me really interested in RL meets computational game theory, because I was working on Monte Carlo CFR, not making any relationship to reinforcement learning. And when I got to DeepMind and I read the chapter on off-policy Monte Carlo, I was looking at the equations and I said, wait a second, this looks like importance sampling. So I asked my colleagues that knew a bit more about RL, and they were like, yeah, of course it's importance sampling. That's what you have to do when you do off-policy. And that's exactly what Monte Carlo CFR is. So in terms of reinforcement learning terms, Monte Carlo CFR is a variant of CFR that uses a behavior policy to sample trajectories. You have to make sure that you sample trajectories with positive probability, otherwise that divide by QZ it's going to do it. I'm fine. And it does the important sampling correction so that your expectation remains equal to the true quantity that you're trying to estimate. So this is really the everything that's driving Monte Carlo CFR. Now this proof is even easier. Okay, so what do we have? Expectation over the sampled counterfactual value. That's just the definition of expectation. We're going to sum over all the blocks, the probability of that block times the value of the counterfactual value of that's given that block. Okay, this we just expanded it. It looks horrible, I know. There's symbols everywhere. All we've done really is taken the definition and put it here. Okay, that's it. We had a QZ in the original definition, but in the expectation we summed over the probability of sampling QJ. So that goes in there. And now this is this. Look at what this thing is summing over. This is the histories in state S, and the terminal histories in Q of J intersect Z. Intersect Z of S. So actually, I'm just going to draw. The easiest way to understand how we're going to just make one line change to the thing to understand how we can get this expectation to work. Okay, so we've got a game tree, state S. Did I do S? I did S. So Z, this thing here is Z of S. It's all the terminal histories for each from S. All the H's are in there. Okay. Now, suppose we had two Q's. Remember, a Q is just a block of terminal histories. So this is like Q1, and this is like Q2, this triangle here. Okay, what matters is the intersection of the blocks and this. So these are the intersections here. All the histories in there. Okay. So what is this thing summing over? This thing is summing over all the possible blocks, and for each block, it's summing over the terminal histories that are in that block that intersect with Z of S. That's this. Now keep in mind, actually, the blocks are allowed to cross over, so let's just actually do that. Okay. And all we're going to do is we're going to change the way that the sum is expressed. So instead of iterating over the Z such that it's in the block J intersect with ZS, we know that the things that we're summing over are always going to be constrained to this region here. Okay, so we can just iterate over all the Z's in there, and for each Z, we can say, what's the list of what's the blocks that assign positive probability to this particular Z, and we can sum over that. That's it. So we just switch the order in which we sum over things, and we get this new expression. So we're summing over these, and for each one of them, that terminal history could be realized by different blocks. So we have to sum over all the blocks such that that terminal history is in that block. Otherwise, it's probably 0. Now, that's it. We're done. This is the definition of that. So that cancels. And okay, so that's Monte Carlo CFR. We are really close. I'm just going to skip this one, and I think we'll take a break now until 4. So I'll just mention what I wanted to, like the third part. I'll share the slides. So if you're interested in actually doing search in imperfect information, there was this extra section that I was going to go through to show that things like Monte Carlo tree search can't be like directly applied to imperfect information games. You have to think about how, like, there's specific problems around it if you do that. Let's skip that because I actually want to get to some of the practical stuff. Okay, so let's take a coffee break and come back here at 4.